هذه حنت غادي نديروا النشيده كبرها باش يبان كبرها باش يبان فهمتيني باش يبان باش ما كيبانوش مزيان صافي حتى في الاخر
السلام صافي Salam alaikum. Bonjour. Donc, Monsieur le Président de l'Université, Madame la Vice-Présidente chargée de la coopération et de la recherche scientifique, Monsieur le Directeur de l'Institut national d'astronomie et de géophysique d'Égypte, Messieurs les doyens et directeurs, Messieurs les vice-doyens, chers collègues, chers conférenciers animateurs de OASA 2022, chers étudiants, honorable assistance. Avant de commencer notre cérémonie, on va écouter l'hymne national. Shukran, merci. Donc, c'est avec un grand plaisir que nous vous accueillons pour cette inauguration de cette 6e édition de l'École internationale d'astrophysique 2022, organisée cette année sous le thème de la spectroscopie. Et nous vous remercions d'avoir répondu favorablement à notre invitation qui coïncide avec la célébration cette année des 15 ans de la création de l'Observatoire universitaire d'astronomie de l'UCAMOOC. Cette école scientifique destinée aux étudiants est unique dans l'université marocaine et co-organisée par plusieurs partenaires, la fac de sciences et techniques de Marrakech, la fac de sciences Smlalia Marrakech, l'observatoire universitaire de l'UCAMOOC, le laboratoire de la physique des hautes énergies et d'astrophysique, ainsi que des partenaires venus des pays amis. Cette école a vu le jour lors de l'inauguration de l'Observatoire en 2007. Sa création a su s'adapter, sa programmation a une plus large palette s'enrichit d'édition en édition et qui est devenu un événement scientifique annuel incontournable. Pour rappel des éditions déjà passées, les thèmes astrophysique générale, planétologie, exoplanètes, satellites et petits corps du système solaire, météorologie de l'espace, a signalé que WASA a accueilli 2 autres éditions, une en 2012 sous forme d'une conférence internationale sur la physique des hautes énergies, au CHEP 2012, et une en 2016 intitulée The First Arab School of Astrophysics, organisée par l'Arab Astronomical Society, dont le siège au Maroc et à la faculté des sciences Mlalia, et dont le président est le professeur Zouhair Ben Khaldoun. Remerciements aux partenaires, à tous les organes de presse qui nous ont accompagnés par des couvertures médiatiques. Remerciements à toutes les personnes qui ont contribué de près ou de loin pour la réussite de cette école. Et nous démarrons avec les discours de bienvenue. Et j'invite le professeur, notre cher ami le professeur Mohamed Oureirt, doyen de la faculté des sciences et techniques, que nous remercions vivement pour son apport et soutien moral et matériel. À vous la parole.
Merci, Monsieur Tariq. Monsieur le Président, Madame la Vice-Présidente de l'Université Qadi Iyad, Monsieur Jad Al-Qadi, Directeur de l'Institut national de recherche en astronomie géophysique, Monsieur le doyen de la Faculté de sciences Smlalia, chers collègues enseignants, chercheurs, chers doctorants, chers invités, sincèrement, c'est un grand honneur pour moi et aussi pour notre établissement, la Faculté de sciences et techniques de Marrakech, d'héberger cette 6e édition de l'École internationale d'astrophysique, nommée WASA 2022, qui va se dérouler du 1 au 8 juillet 2022, qui s'intitule cette année la spectroscopie en astrophysique et qui est organisée conjointement par la faculté de sciences et techniques, par la faculté de sciences Smlalia. Et bien sûr, lorsque je dis Smlalia, c'est le laboratoire de haute énergie en astrophysique et aussi l'observatoire de UCAMOOC. Nous sommes sincèrement heureux de vous accueillir et de remercier l'ensemble des participants que nous font l'honneur de partager avec nous durant 6 jours leur savoir et qui nous viennent de pays amis. Je ne veux pas citer tous, mais en particulier l'Égypte, bien sûr le Sénégal, l'Éthiopie, etc. Sans oublier bien sûr les enseignants et les doctorants marocains, et en particulier ceux de l'université Qadi Iyad. Cette manifestation est l'une des manifestations qui est devenue une tradition et aussi une activité phare de l'Observatoire et de laboratoire de haute énergie de la faculté de sciences Smlalia. Après, bien sûr, comme il a dit M. Tariq, le succès des précédentes éditions, et on est cette année à la 6e. On ne peut que se féliciter à l'université Qadi Iyad d'avoir cet observatoire d'Ukaimden au niveau de l'université Qadi Iyad. Je veux féliciter aussi les équipes de recherche impliquées, surtout dans cette thématique, et qui sont à l'origine de l'observatoire, bien sûr, et surtout des initiateurs de sa création au niveau de l'UCA. Et comme vous le savez, il regroupe des chercheurs de renommée, reconnus à l'échelle nationale et internationale dans sa thématique. Cette école réunira autour des thèmes retenus les scientifiques universitaires et doctorants de nos établissements pour partager et discuter de l'actualité de la recherche dans ce domaine. Le choix de la thématique qui est la spectroscopie en astrophysique de cette école, qui, comme les précédentes, ne manquera pas de laisser un fort impact pour asseoir définitivement cet axe de recherche à l'UCA. Les sujets qui seront abordés durant ces journées sont éloquents, à plus d'un titre, sur l'importance de vos travaux et bien sûr les perspectives de leur application, à savoir la spectroscopie d'étoiles variables, la spectroscopie des objets géocroiseurs, la vitesse radiale pour les exoplanètes, l'instrument de la spectroscopie et les séances pratiques, bien sûr, de traitement de données. Comme vous le savez, l'astrophysique est traditionnellement une science de l'observation dont les progrès sont directement liés aux évolutions et aux progrès technologiques, mais je pense qu'il est nécessaire de confronter les observations à des modèles numériques, théoriques ou physiques qui seront développés, qui se développent au sein des laboratoires. C'est pour cela la recherche dans ce domaine au niveau des laboratoires et aussi la formation universitaire pour les jeunes chercheurs est plus que jamais nécessaire dans ce domaine. Cette manifestation est certes l'occasion de faire le point sur les travaux actuels de recherche dans ce domaine, mais elle est aussi l'occasion de constituer des réseaux de complémentarité scientifique, d'échange de données et de mutualisation, bien sûr, de moyens et humains et matériels. Cette 6e édition de l'école de la spectroscopie en astrophysique sera marquée par la signature d'un accord cadre de coopération entre l'Université Qadi Iyad et le National Research Institute of Astronomy and Geophysics, NRIAG, dans notre pays ami d'Égypte, dont le responsable est avec nous aujourd'hui. Certes, cette collaboration va permettre le partage entre les équipes impliquées et qui seront impliquées davantage à travers des actions comme la mise en place de projets en commun, la mobilité des chercheurs, que ce soit étudiants ou enseignants-chercheurs, pourquoi pas la codirection de thèses dans ce domaine, la mutualisation du moyen, parce que, comme vous le savez, en astrophysique ou en astronomie, les moyens, c'est des appareils ou des moyens qui sont lourds et qui coûtent trop cher. Et donc, la mutualisation est d'une grande importance pour, bien sûr, amortir tout ce qui est investissement en appareillage. Et je pense que cette convention aussi va permettre d'élargir la collaboration, non pas tout simplement en astronomie, mais aussi dans d'autres domaines complémentaires, si j'ose dire, à savoir la géoscience, la géodynamique, et je pense que l'Université Qadi Iyad, dans l'Université Qadi Iyad, on retrouve des chercheurs, des anciens chercheurs qui s'intéressent à ces domaines. Cette rencontre n'aurait pas pu avoir lieu, bien sûr, sans l'initiative de nos enseignants-chercheurs et leur abnégation dont ils ont fait preuve, et aussi sans la confiance qu'ils ont su susciter chez nos partenaires, que ce soit au niveau national ou au niveau international. Je ne voudrais pas prendre beaucoup de temps de votre temps précieux. Pour conclure, je tiens à remercier le comité d'organisation de OASA, de la FST et de la FSSM, et aussi les doctorants. Je tiens aussi à remercier tous les intervenants nationaux et internationaux qui ont voulu partager avec nous leurs travaux de recherche. Et je vous souhaite beaucoup de succès dans vos travaux et bien sûr un agréable séjour à Marrakech. Et merci.
Merci infiniment, cher doyen. Aussi, nos remerciements les plus chaleureux à notre cher président, professeur Walid Hassan Habib, pour son soutien moral et financier pour réussir cette école. Et donc, je passe la parole au professeur Gad El-Qadi, le directeur de l'Institut d'astronomie et de géophysique en Égypte. Ustad, lakum al-kalima. Lakum al-kalima.
صباح الخير عليكم جميعا. I can't speak French, but if you allow me, I can speak in English because we have other international guests. First of all, good morning, everybody. It's my pleasure to be here today with you for my first visit ever to Morocco and the first as well to Marrakesh. I'm here for different reasons with different entity. As a president of the National Research Institute of Astronomy and Geophysics in Riyadh, as well as a president of Arab Association of Astronomy and Geophysics, one of the technical arm of Arab Leagues working in astronomy and space science. We have long term of discussion about collaboration with Qadi Ayad University, our colleague from UCAMOOC Observatory, and we have been jointly working with Astrophysics School, either the international one here or Arab one in Egypt. But we thought it's better to have a higher umbrella of agreement between both Riyadh and Qadi Ayad to make a better chance for our colleagues to work together. I would like to thank Mr. President and wish him a very speedy recovery. And I would really looking forward to meet you very soon, either here or in Cairo. بلدك الثاني أهلا بيك يعني ونتمنى لك الشفاء العاجل إن شاء الله. In brief, in Riyadh we had started since 1839, so almost 200 years. We started as a little astronomical observatory to calculate the prayer time and Hijri calendar, Arab months, not only in Egypt, but for Arab region at that time. Then it was expanded to include many specialty in astronomy, astrophysics, space science, solar physics, and of course, renewable energy as well. Then by 1889, we started the first seismological station in Africa and Middle East. It was one of the 20 stations worldwide. Both astronomy and geophysics had a lot of contribution. Early 90s, we had observation for different comets, one of them Halley comets. We recognized for the first time Pluto and many other achievements, including the first landing of human-inhabited satellite space shuttle, Apollo 11, on the moon. This was 1969, probably before birth of many of you. And then we're working with all facilities we have. Currently, observatory optical telescope of 74-inch, that's in Katamiya. And it was my pleasure to receive many of our brothers here and our international colleagues as well, several times at Katamiya. Our utilities and facilities are available for all community to use. You know, astronomical facilities, telescope, and this is not a cheaper one, is not available for everybody in the world. So once an institution or a country has observatory, it can be available for any one of the international community to use it. The same for geophysics. We have a lot of collaboration with colleagues from here, Muhammad Premier University at Wajda, Scientific Institute of Muhammad Al-Khamis. And I hope this time also will trigger our geoscientists from both Nariaj and Kada Ayad to start our collaboration. Through all facilities and our personnel, our staff, we have a lot of capacity building program within Egypt, regionally with Arab and African brothers and colleagues. And we have also some international programs in both astronomy and astrophysics, space science, and geophysics, including all disciplines that Nariaj has research and facilities. Out of this capacity building and outreach training course, specialized school in astronomy, astrophysics, seismology, geodynamics, applied geophysics, and archaeology as well. That's why I'm here to invite all of you to have a direct link with our staff, to have joint research, joint collaboration, participate together in a conference or a meeting. And thanks for COVID pandemic, it make it available to be in direct communication with people online without يعني تعب السفر ومشقة وصعب التمويل. So it became now available at any time you have a Zoom meeting, as we have now with this international school, many members not available in the room, even not in Marrakesh, like السيد زهير هو حاليا في الخارج ولكن مشارك معنا اونلاين في الزوم. So again, I would like to thank everybody here in Kada Ayad for giving me this opportunity to be here today with you. We are ready to collaborate, as my friend mentioned, in different aspects, including joint degrees, double degrees, mobility programs, workshop, training course, even with those of astronomy, astrophysics, joint observation, using facilities here and facilities at Nariaj in Egypt. And also we can go in trilateral or multilateral collaboration, including our colleagues here in this international schools, and who are also not here today, they're welcome to join us. And an example of the conference we are doing, since we are talking about astrophysics and astronomy, we are hosting and organizing the 6th MIRAM conference, which is Middle East and Africa regional IAU conference that will be next year, February. So the flyer and the brochure will be available here. Any of you are welcome. On the other side, for geoscience, we are hosting and organizing the General Assembly of Asian Seismological Commission and African Seismological Commission, that including geodynamics, natural hazard, that will be on Hurghada this October. So any one of you are welcome to join and contribute to this one, since we need to come together to exchange our ideas and views, how to enhance our research and how to get some benefits to our community suffering from many crises, COVID and many other international economic crises. So we have to play our role as scientists and scientific organization and institution to tackle a lot of these challenges and afford our communities some good solution. Thank you very much, and I wish you a very successful international school. And would like to welcome also to, I'll invite you to our schools in Cairo. That one will be in October. My colleagues, Ben Heda and all of them are contributing, and Said Zuhair also. And I'm available all the time together with you for any question or comment, and my colleagues here during the school. شكرا جزيلا وأتمنى لكم كل التوفيق والسلام عليكم ورحمة الله وبركاته.
شكرا أستاذ. الكلمة الأستاذ حسن المدن عميد كلية العلوم السمنالية، تنشكروه على المجهودات وعلى السوتيان ديالو مورالي ماتيريال. افو لا بارول.
Merci. Merci, cher Tariq. Monsieur le Président, Monsieur le Directeur of National Institute of Astrophysics and Geophysics of Egypt, Madame la Vice-Présidente, chers collègues, Monsieur le Doyen de la Faculté de Sciences et Techniques, chers collègues, membres du laboratoire et organisateurs de cet événement, de cette école, chers professeurs, chers collègues, chers étudiants et honorables assistance. C'est un grand honneur aujourd'hui pour moi d'assister à cette séance d'ouverture de l'école internationale organisée par l'Observatoire de Camden. À cette occasion, je profite donc pour féliciter les collègues qui ont déployé tous les efforts pour une bonne organisation de cette école, qui montre en fait l'engagement des collègues aussi bien de la faculté des sciences Milalia que de la faculté des sciences FST, puisque plusieurs membres ou bien plusieurs collègues sont membres du même laboratoire. C'est une très bonne chose qui montre leur engagement plus envers la recherche dans le domaine et leur participation ensemble à l'amélioration et le développement de cette discipline qui est l'astrophysique et qui est les hautes énergies. Donc le laboratoire, il fait beaucoup d'efforts pour l'organisation de plusieurs événements, mais également de plusieurs projets de recherche qui sont très importants dans le domaine. Et le résultat, c'est que l'Observatoire de Camden, il représente actuellement, il a une renommée internationale et a participé à plusieurs découvertes dans le domaine de l'univers, ce qui représente donc un grand intérêt pour nous au niveau de l'université Khadayad, mais également au niveau des établissements qui soutiennent fortement ce centre, ou bien cet observatoire de Camden. Donc je profite de cette occasion pour les remercier encore une fois pour cette organisation. Je remercie également tous les collègues et chercheurs qui sont venus de loin pour contribuer et participer à cet échange, à cette école, qui va permettre un échange, un partage de la connaissance, mais également une transmission de tout ce qui concerne la spectroscopie qui représente au niveau de cette 6e édition. Donc l'intitulé qui est la spectroscopie. Donc je ne vais pas trop tarder. Monsieur Taourir, il a largement parlé de tout ce qui concerne de cette école, le programme et tout. Je vous souhaite une bonne continuation et je vous souhaite une bonne formation et un grand échange. C'est vraiment une très très bonne occasion parce que l'idée d'organiser cette école à l'UCAMOOC est aussi une très très bonne idée parce que ça va permettre aux collègues de se concentrer, d'avoir un échange continu pendant toute la journée. C'est vraiment une très bonne occasion pour l'ensemble et je vous souhaite un bon séjour à l'UCAMOOC et une bonne organisation à nos collègues que nous soutiendrons et nous soutenons toujours fortement. Merci à vous.
Merci, cher doyen. La parole à notre cher ami, le professeur Mohamed Chabab, qui est le directeur du laboratoire de la physique des hautes énergies et astrophysique. À vous la parole.
Assalamu alaikum. So, honorable guests, respected President Moulay Hassan Ahmed, respected deans of our faculties, Faculté des Sciences et Techniques and Faculté des Sciences Milalia, ladies and gentlemen, as director of High Energy and Astrophysics Lab, I'm here very delighted to be here today for the opening of this landmark international school. On behalf of my lab and the local organizing committee of my university, I'm pleased to welcome all of you to Qadi Ayyad University and to Morocco. Since the first edition in 2007, this school provides a unique opportunity for graduates students and young researchers to strengthen further their backgrounds in astrophysics and astronomy in many selected topics. This edition, the sixth one, is dedicated to spectroscopy in astrophysics under the supervision of several international researchers and experts in this field. I will be brief in my speech, just to give some overview on High Energy and Astrophysics Lab, which is composed of two research teams. One is working on many topics on high energy physics, doing some phenomenological calculation, theory modelization, working also on some problems in strong gravity, mainly related to black holes and their thermodynamics, but also some people in my lab are working on nuclear theory, theoretical aspects of nuclear theory, essentially on collective motion in nuclei. And the other team, as you know, is working on astronomy, astronomical observation, but also doing some astrophysical, working on some astrophysical open problems. And of course, with the UCAMOOC Observatory under the supervision of Professor Zuhair Ben Khaldoun. As I said, I'll give just an overview. I will be brief in my speech here. So I wish you all a very fruitful school and hope you all have a pleasant stay in Morocco and in Marrakesh. Thank you all for your presence and participation. شكرا على المشاركة والحضور إلى المغرب.
Merci, cher ami, cher collègue, professeur Shabab. Donc on passe au mot de notre chère Catherine Colombert. Donc ça sera online.
Bonjour, est-ce que vous m'entendez?
Department Bureau, yes. Okay.
Yes. Can you also see me? Yeah, I'm sharing my screen as well, so I don't know. I see a picture of myself. But dear esteemed colleagues, dear officials of the university and of representatives of science in Morocco, dear colleagues and dear students, very warm welcome to this Waza school. I had hoped to be with you, but COVID decided otherwise. I'm still in quarantine, but I hope to be out of it before the end of the school because I've already been sick for a week. But unfortunately, I couldn't be here in time. So I am happy to welcome you to this school. And I want to say a few words about the collaboration that also contributed to this school. I met Professor Menhida and Professor Sefiani at a conference several years ago, and they are very prolific scientists in the fields of variable star research, which is also my research field. And so I got to know the fact that Morocco has a very, very prolific observatory, and that the observatory of UCAMOOC is one of the most important ones on the African continent. Since we have common research interests and also interest in both scientific education, scientific development, using astronomy as a tool for development and STEM education, we decided to collaborate because, as you know, astronomy is really a gateway science. Astronomy is a science that really speaks to many people of all ages and that can also attract young people to study subjects in science and technology. And this is something that we also want to stimulate all across the world. And so we wrote a project. You see in my background, there is the logo of VLIR UOS. Actually, we got funding for an exchange project between Belgium and Morocco. And we involved Senegal in this because on the African continent, Morocco is playing a very important role, having such an important observatory that contributes to scientific discoveries that are really very important in exoplanets, in solar system research, in variable stars. We want to have Morocco also be an important hub on the African continent. And this is also exemplified in the school right now, where people from different African countries are attending. And we're actually, it's an international, a global meeting. So this VLIR-US project has as a goal exactly to strengthen scientific collaborations and also to use astronomy as a tool for development, for enthusiasming young people to do STEM, and also raise awareness environment, because as you know, UCAMOOC is a site that has a very clear sky and where there is very little light pollution and air pollution. And this is something that should be cultivated and kept that way. So thanks to this project, we could have very fruitful exchanges in the past 3 years. It was supposed to be 2 years, but because of COVID, the project was extended. And this is actually the final event, a final school within the current project. But we hope to expand this collaboration to the future because during the project, we actually thought about it would be nice to continue this because the collaborations are going well. And in the course of the project, we also took part in the conception of new project applications that involve the wider African continent, in which some of you are parts. And so what we also want to further explore is to expand the UCAMOOC Observatory with a new facility, a robotic facility that can act as a prototype for other robotic facilities across the African continent and even globally. So this is also something that we would love to discuss with all of you this week. And spectroscopy, of course, is a part of astrophysics that can contribute widely to any kind of research in astrophysics. So we want to explore facilities of both photometry and spectroscopy, how they can intertwine with each other, and how with a small facility, a small telescope, you can contribute to top-notch research. And with this, I wish you a great start of the school. I dearly hope to meet you in the coming days. If possible, I will try and join you on site. And in any case, I hope to see you very soon online or in real. And have a great start. Thank you very much.
Merci notre chère collègue Catherine. Et nous avons reçu un mot de notre ami, collègue, professeur Zouhair Ben Khaldoun, le directeur de l'Observatoire. Malheureusement, il n'a pas pu être parmi nous, il est en déplacement. Donc, son mot sera lu par Mariam Gennoun, docteur en astrophysique et musicienne.
Bonjour. Donc, je suis mademoiselle Mariam Gennoun et je vais vous lire le mot d'ouverture de monsieur prof Zouhair Ben Khaldoun, le directeur de l'Observatoire de l'UCAMOOC. Merci. So, dear students, dear speakers, Mr. President, Mr. Director of NRIAG, Madam Vice President, Deans, member of the Organizing Members Committee, and dear colleagues. Allow me first of all to apologize for not being with you for this launching ceremony of the WASA School, but I will join you, if all goes well, tomorrow at the Observatory of UCAMOOC. I would like to express my sincere thanks to all of you for your presence and for your contribution to the organization of this event, which is of great importance to us. We have indeed for a long time at Qadi Iyad University decided to invest in the training component to meet the challenges of the introduction of the astrophysics team in Morocco and its development in the MENA region and Africa. For this, the Laboratory of Physics of High Physics Energy and Astronomy and the UCA have decided since the inauguration of the UCA in 2007 to organize regular seasonal schools in astrophysics. We have thus organized 5 editions of WASA schools, but also since 2016 in the creation of the Arab Astronomical Society, ARAS, we have been the main partners in the organization of 6 other schools called ARAS SFA in the region. 2 editions in Morocco in 2016 and 2017, 1 in Lebanon in 2018, 1 in Egypt in 2019, 1 in virtual mode in 2020 and another in 2021 in Qatar. We have also decided to launch, still on the initiative of ARAS, an advanced school in astrophysics with our partners from NRIAG, whom I would like to warmly thank in the person of Dr. Gad Al-Qadi here present among us today. Spectroscopy is an important tool in several fields of science and astrophysics in particular. The study of the interstellar medium of the evolution of variable stars, of the nature of galaxies, of nebula and other stellar objects, as well as the detection of exoplanets, and the study of the atmospheres constitute as many fields of investigation where spectroscopy is of great contribution. Since 2010, the UCA has invested in this team by equipping itself with a spectrograph of modest size, but which has already given very good results and several publications taking advantage of the exceptional quality of the UCAMOOC site. We have therefore decided to choose this theme for the present school, hoping in this, the consolidation of this theme within our region, but also to strengthen the international cooperation of the UCAMOOC Observatory and the LPHEA for spectroscopy in astrophysics. As usual, and on the sidelines of school, we are organizing several awareness-raising events for the general public in this year. A special mention will be given to inclusion through astronomy by going to organize events on the benefits of young rural girls in astrophysics. Good wind for WASA 2022 and see you soon. Thank you.
Merci Myriam. Donc la parole à notre cher ami et collègue le professeur Abdelmjid Ben Hida, qui assure la coordination de cette 6e édition WASA 2022. À vous la parole.
شكرا. نبدا نهضر بالدارجه المغربيه. مرحبا الرئيس، مرحبا الرئيس ولا كيهضر من المغربيه اكثر منا دابا. سياد الاخوان المصريين، الاخوان الشقاء العرب من الامارات، من قطر، من تونس، كنرحبوا بكم. نتمنى لكم سفر سعيد وفي مقر في لوكيمدن. حنا كنرحبوا بكم. هي تجربه انسانيه اكثر. هادشي اللي كنتمناو في الاخر. Just I will move to English, so I want to thank and say welcome to our speakers, our Anglophone students, and I have a special thank to my roomie, Professor Andy Segonsky, who's always support us, and he's from USA, and I will thank him a lot. Je reprends donc en français maintenant pour nos collègues français, et c'est vrai que je veux pas revenir. Bon, j'ai pas préparé de mots, Mais je veux vraiment revenir sur 3 volets pour cette école. L'organisation, c'est vrai, dans les conditions difficiles, ça a été normalement initié pour la version de 2020. Et donc, vu les conditions difficiles de Covid, on a eu du mal jusqu'à la dernière minute pour annuler. Mais c'était que chose remise, et donc on a vraiment bataillé, tenu pour que cette session soit faite. Et donc, effectivement, on l'a eu. Alors, pourquoi? Parce que vraiment, alors je dis pour les 3 volets. Le premier, bien sûr, c'est pour nos étudiants africains, pour nos étudiants étrangers. Donc, cette transmission de savoir, ce partage, donc, et on est fiers des dernières techniques qu'on peut avoir en astrophysique. Et je vous informe, pour les gens qui ne connaissent pas, que nos étudiants, ils ont rien à envier aux étudiants étrangers, et vraiment on est fiers d'avoir des exemples comme M. Moulin, qui est donc en postdoc aux États-Unis. Donc, et ça, c'est un reflet d'une bonne formation qu'on effectue au sein de Qadayad. Donc, le volet recherche, ça se fait, c'est vrai. Bon, on a une manip spectroscopie qui n'a pas cessé d'évoluer. Et on est fiers parce que, bon, comme vous savez, il y a beaucoup de programmes internationaux au sein de l'Observatoire, mais on est fiers de notre bijou qui est à 100% Université Qadayad. Il y a le projet Villarios, on l'a fait évoluer, et donc c'est très important au niveau de recherche. Alors, en plus de l'instrumentation, bien sûr, il y a des projets qui sont en cours. Alors, on a postulé pour plusieurs projets. Alors, surtout, on privilégie maintenant la coopération sud-sud entre collègues africains. Et donc, via des projets avec soit les Européens comme Horizon. Et donc, là aussi, on attend à ce qu'on connaît des projets qui seront financés. Et comme il a dit Catherine, on a initié un projet, un prototype qu'on va commencer, un télescope qui demande un minimum de logistique et qui va être étalé à 15 pays africains. Et donc là aussi, c'est vraiment c'est des idées qui sont initiées à travers des rencontres. Et c'est pour ça, c'est vrai, en plus de la dimension d'échange de savoir, il y a vraiment ces expériences qui sont humaines. Alors, par exemple, je remercie Claudine, qui est là depuis 10 ans, une dizaine d'années, qui est responsable de MOS. On avait partagé un repas, en parlant de l'Aïd, on avait partagé les brochettes en 2011. Ça a tenu toujours une bonne relation. Avec Catherine, ça a évolué, mais c'est ces échanges. Maintenant, comme Catherine, il a eu le Covid malheureusement, mais je pense à son fils Yoram qui l'oblige à venir, qui insiste pour qu'elle soit parmi nous. Une autre collègue espagnole, Mariana, qui insiste de venir pour assister à l'observation qu'on va faire ce soir avec les talibans. Et je tiens vraiment à ce volet qu'on développe en parallèle avec l'école, c'est la sensibilisation à l'astronomie et la sensibilisation aussi à la participation de la fille rurale à la science. Et donc, je vous informe qu'on est très content, on est très honoré de faire nos partenaires changer avec ces filles du milieu rural. Donc, normalement, on a ce soir une soirée avec Dar Taliba à Marrakech. Et mardi, on a aussi avec Education for All dans un village à Tinmel. Donc, voilà aussi, et on a 2 conférences grand public. Donc, tout ça, normalement, on aura comme programme, ce riche programme pour OASA 2022. Donc, finalement, je dis à nos étudiants, à nos speakers, bienvenue, welcome, marhaban, shukran. Merci beaucoup.
Merci, cher collègue Sir Abdelmjid. Et on passe la parole à notre cher président, professeur Moulay Hassan Habed.
Bonjour. Vous m'entendez?
Oui, oui, c'est bon.
Bien. Messieurs les doyens, Madame la vice-présidente, Monsieur le directeur de l'Institut de l'astrophysique et de la géophysique en Égypte, Monsieur Gad El-Qadi, bienvenue à Marrakech. Monsieur le directeur du laboratoire des hautes énergies et l'astrophysique, Monsieur les vice-doyens, chers collègues, chers participants et participantes, chers étudiants et étudiantes, bienvenue à cette 6e édition de l'école OASA. Bien entendu, je suis heureux que cette périodicité de l'école reprenne parce qu'il était empêché et arrêté par le Covid. Mais je suis donc heureux que cette activité redémarre parce que c'est une activité très intéressante à l'échelle de l'université et c'est une activité qui fait partie et qui anime une thématique forte et très importante à l'échelle de l'université. L'université, comme vous le savez, était et reste toujours avec un rôle de prodiguer le savoir et de se positionner comme un lieu de réflexion. En fait, ce qu'on a assigné à l'université, c'est de prodiguer le savoir et de se positionner comme un lieu de réflexion. Mais je pense que ce temps est révolu. L'université s'est vue changer d'esprit et de rôle. L'université aujourd'hui est un acteur majeur de son territoire. Il va vers le sens de l'autonomie dans son fonctionnement, ce qui lui confère la latitude d'agir en interne comme vers l'extérieur, d'être un espace connecté et ouvert, d'impulser et d'accélérer idées et projets innovants. L'université a longtemps été critiquée pour son mode de fonctionnement, confrontée aux multiples défis d'un environnement en pleine mutation, notamment sur le plan économique et technologique. Il est aujourd'hui capable de se réinventer, de trouver les chemins d'une nouvelle manière d'agir. Le nouveau management public fait partie de ces outils que l'université se doit de saisir pour faire face aux multiples problèmes qui entravent l'exercice de son rôle. L'interaction grandissante de l'État et de l'économie doit se faire prendre conscience de la nécessité de nouveaux modes de décision. L'efficacité, l'écoute ou encore l'interaction sont désormais indispensables pour répondre aux demandes. Il s'agit de dépasser les approches rigides et archaïques qui ont longtemps gangréné l'université. Notre ministère de tutelle est comme nous conscient de la nécessité de l'autonomie et du renforcement de l'indépendance des universités à l'instar des modèles internationaux. Le principe de l'indépendance va vers le sens de la contractualisation. Il s'agit pour l'université d'assumer pleinement ses responsabilités dans un environnement marqué par la concurrence entre l'université, non seulement sur le plan national, mais aussi à l'échelle internationale. L'université doit donc repenser sa gouvernance. Ceci revient à entreprendre un ensemble d'actions liées, entre autres, à revoir les structures de gestion, à l'instauration d'un organe central de décision, à la mise en place de l'agilité, de la culture du changement à l'innovation. Ceci revient également au soutien du développement des compétences, aux nouvelles formes d'organisation, au partenariat avec des entreprises innovantes, à la mise en place des Fab Labs, au soutien des startups, à la mise en place d'incubateurs en interne ce que nous ambitionnons à matérialiser par le biais de notre cité d'innovation. L'Université Al-Qadir Iyad, à travers sa stratégie de développement, a développé des axes stratégiques en adéquation avec les nouvelles missions édictées par les changements que connaît le monde et les transformations de l'économie du savoir, des axes qui lui permettent de se concevoir en tant qu'entité entrepreneuriale. Ces axes stratégiques s'articulent autour de l'efficience managériale qui matérialise la volonté de l'université de mise en œuvre d'actions basées sur la concertation, la décentralisation, la déconcentration. L'efficience managériale implique les pratiques de bonne gouvernance qui s'appliquent à l'ensemble des volets de la mission de l'université, à savoir l'enseignement, la recherche, la gestion administrative, ainsi que le budget. La digitalisation, l'Université Qadir Iyad réaffirme sa volonté de poursuivre la politique ambitieuse de la transformation digitale menée depuis plusieurs années et de considérer le numérique comme un levier de progression. L'intégration du numérique dans un système universitaire est devenue aujourd'hui une évidence. Ainsi, l'UQA s'engage dans la digitalisation de ses pratiques dans la pédagogie, la recherche et l'administration. L'internationalisation. Votre école en est un exemple. Le travail que fait l'Observatoire de l'UCAMOOC et du Laboratoire des hautes énergies et de l'astrophysique en est un autre exemple de l'internationalisation et de la coopération internationale à l'échelle de notre université. Donc l'université s'inscrit dans une dynamique d'ouverture sur le monde par le biais de sa politique d'internationalisation. Une telle ouverture implique forcément des exigences structurelles d'alignement sur les standards internationaux. L'UQA exprime cette ouverture à l'international à travers la restructuration de sa politique d'internationalisation tout en consolidant la place qu'elle occupe au niveau national et international. L'ancrage territorial qui matérialise la volonté de l'Université Qadir Iyad d'adhérer à la dynamique du développement de la région où elle s'ancre. Il s'investit dans des formations, les recherches et l'expertise qui répondent aux attentes de son environnement socio-économique, réoriente ses thématiques prioritaires vers les thématiques cruciales de la région de Marrakech-Safi. L'ouverture sur le monde socio-économique permet l'optimisation des possibilités d'emploi pour les lauréats, des lauréats formés aussi bien techniquement que dans des compétences transversales, et ce, dans des conditions d'équité, de parité et d'inclusion. Je crois que l'Observatoire de l'UCAMOOC est un lieu, est une structure qui peut pleinement jouer un rôle fondamental dans l'ancrage territorial de l'université dans son environnement économique et social, dans le sens où l'UCAMOOC ou l'Observatoire peut jouer un rôle fondamental dans le développement socio-économique de la région d'UCAMOOC. Mesdames et messieurs, ces orientations stratégiques permettent à Qadir Iyad de marquer une réelle transition d'un mode pédagogique axé sur l'enseignant vers un mode d'apprentissage centré sur l'étudiant en intégrant des nouvelles approches pédagogiques qui permettent à l'étudiant, qui mettent l'étudiant au centre de ses préoccupations. Ainsi, Qadir Iyad vise l'acquisition par des apprenants de compétences entrepreneuriales et des compétences en recherche, des compétences émotionnelles universelles qui permettent aux lauréats d'acquérir des capacités à repenser, agir, anticiper et envisager des solutions alternatives à des scénarios qui font le quotidien des entreprises. En plus du savoir-faire, l'enseignement à l'Université Qadir Iyad intègre des modules généralisés de soft skills susceptibles de traduire chez le lauréat universitaire des savoirs comportementaux. Il s'agit de compétences émotionnelles, d'adaptabilité, de créativité, d'optimisme, d'intelligence émotive, de pensée critique, de flexibilité cognitive, de jugement, de négociation, d'ouverture d'esprit, de travail en équipe, etc. Des compétences recherchées par le monde socio-économique qui nous a confié leur carence chez la majorité de nos lauréats. C'est ainsi que l'UQA a consacré 20% de tous les contenus de ses masters et licences professionnelles aux langues et cultures et compétences transversales, développement personnel, projets professionnels, activités associatives, tutorat, sport, etc. Il a fait appel à des coachs sélectionnés à l'échelle nationale et des enseignants de l'Université Qadir Iyad qui ont été formés sur les programmes soft skills à dispenser et certifiés par l'université. Mais il n'y a pas que ça. L'université consacre aussi plus de 20% de son budget à la recherche scientifique. La thématique de votre rencontre est parmi les thématiques phares de notre université. L'université ne cesse et continuera à soutenir le développement de cette thématique qui fait partie des thématiques intéressantes et importantes, productives de notre université. Et il continue aussi à œuvrer pour que l'Observatoire de l'UCAMOOC joue un rôle plus important dans le développement régional et soit un lieu attractif et d'animation scientifique et culturelle. La signature de la convention aujourd'hui avec l'Institut de notre pays frère, l'Égypte, et dont les objectifs sont au cœur de la stratégie de notre université, est une chose très importante auquel nous donnons nous souhaitons donner plus de visibilité et accompagner à l'échelle de la présidence pour la mise en œuvre de ces objectifs qui sont au cœur de la stratégie de l'UQAM. Je tiens, pour terminer, à remercier d'abord tous les participants qui ont répondu positivement à notre appel malgré les conditions de la pandémie qui continue encore et dont la 7e vague est en train de nous envahir. Je remercie le comité d'organisation, tous les responsables du laboratoire des hautes énergies et de l'astrophysique, les responsables de l'observatoire de l'UCAMOOC, et je vous souhaite grand succès à vos travaux. Et je trouve déjà que les initiatives qui sont prises en marge du programme scientifique de l'école Waza constituent une grande portée vers le développement de la région et vers le rôle que doit jouer l'observatoire de l'UCAMOOC et le laboratoire des hautes énergies, qui est un petit peu le socle de ce laboratoire, et que peut jouer les sciences de l'astrophysique et de l'astronomie pour l'épanouissement et l'ancrage de l'université dans sa région. Merci à toutes et à tous et bienvenue à nos invités. Je vous remercie et je regrette de ne pas être avec vous. Je suis l'un des premiers victimes de cette 7e vague. Je vous demande de reprendre vos bavettes, de faire attention à vous-même et à vos proches. Merci.
Merci, cher Président, pour ce mot précieux et riche. Et avant de passer à la signature de la Convention, je tiens à féliciter, à remercier les jeunes, les étudiants, le club des étudiants de la FST et de la FSSM pour tous les efforts qu'ils ont fournis pour réussir cette édition. Et je vous demande de les applaudir. Alors là, on va passer à la signature de la Convention. Donc, Madame Fatiha, notre cher collègue que nous remercions aussi pour l'effort qu'il a fourni.
Faites semblant de signer.
بهذه المناسبة طبعا بشكر السيد الرئيس وبتمنى لحضرتك يعني تمام الشفاء، وإن شاء الله يعني يتم تفعيل الاتفاقية بشكل رسمي قريبا. وبهذه المناسبة بنهدي درع المعهد للجامعة. أيضا هناك هدية بسيطة للجامعة، يعني حاجة تذكار للحضارة الفرعونية، طبق فرعوني عليه يعني المرأة، بما أننا بنتكلم عن دور المرأة في المجتمع، ويعني من قدم التاريخ والمرأة في مصر لها دور عظيم، تقلدت الحكم وكانت ملكة وكانت حاكمة للبلاد، فده يعني تذكار بسيط للجامعة.
شكرا جزيلا.
فرصة يعني نائبة الرئيس الدكتورة فاطمة أيضا امرأة.
ولقد لعبتم على وتر أحبه جدا. وكذلك إذا تفضلوا السيد المدير تفضل بأخذ كذلك تذكار من جامعة القاضي عياض عربونا للصداقة وعلاقات الصداقة والأخوة ما بين جامعة والمتميزة بين مصر الحبيبة والمغرب، وكذلك بين إن شاء الله تكون بداية شراكة مثمرة ما بين معهدكم وبين جامعة القاضي عياض. شكرا جزيلا في علوم القضاء ولكن في علوم أخرى. شكرا جزيلا. هذا فقط تذكار من مراكش.
شكرا جزيلا.
يعبر عن تقنية وإبداع الصانع المغربي.
شكرا.
الصانع التقليدي المغربي.
شكرا. ممكن تسمحوا لي أيضا يعني تقديرا للنشاط اللي بيقوم به مرصد كوميديان والأخوة في المرصد. بنفتقد السيد زهير إنه مش موجود معنا اليوم، يعني تذكار كده بسيط من المعهد لمرصد كوميديان.
شكرا جزيلا دكتور جاد.
نطور تعاون علمي مثمر للبلدين
ان شاء الله
خلال تبادل الخبرات على مستوى الباحثين وكذلك الطلاب من مصر ومن المغرب
ان شاء الله. هذا املنا وهدفنا ان شاء الله. شكرا جزيلا.
شكرا جزيلا.
شكرا سيادة الرئيس. شكرا لحضرتك.
شكرا جزيلا دكتور جاد.
Alors, je vous invite pour une photo d'ensemble.
شكرا جزيلا.
واحد الصورة جماعية ديال الناس كاع اللي في لونفي. Une photo de groupe, s'il vous plaît. Je demande à Césaire Ben Khaldoun s'il est encore avec nous d'essayer. Accès aux caméras, s'il vous plaît, Si Ben Khaldoun.
invité pour un pause café. Vous y allez ensemble.
Vous êtes invité à une pause café. Pour combien? Pour une demi, pour combien? 15 minutes? 15 minutes. 15 minutes pour reprendre les conférences, s'il vous plaît. 15 minutes. Merci.
Recording stopped.
كاين شي حاجه عافاكم معايا المشكله ما كديرش اصاحبي 2 مينوت اللي ما بغاش راه يمشي راه صافي ايوا اندرو رجع التيتر عافاك هو غادي نشوف غير لو تيتر ديال ما عقلتش لو تيتر ديال وي خلي غير نشوف سبيكتر تاع Comment tu le ton nom
Recording in progress.
لا لا بلاتي غنعرف is the first one, the first course.
Okay. Yeah, that's on the 4th, the 5th of July.
Okay.
And then that's about exoplanet spectroscopy. Grateful for her first talk, and then she'll talk about it very specific. So that'll go really well.
C'est bon? I think that all students are here. Should we begin? Okay, لا 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 2 minutes. 2 minutes and après je rentre. Okay. So the first course in School WASA 2022 will be given by our friend Professor Andrew from Harvard Smith Sonian Center for Astrophysics. So the first course is about spectroscopy theory. So directly I give can begin. Thank you very much, Andrew.
It's a pleasure to be back.
Go ahead.
Oh, thank you. So can I take that? I'll do it. So I was trying to think, spectroscopy theory covers a lot of ground. And, the books on spectroscopy are, you want to advance them? Because there's some, okay, we'll do it that way. Okay, it's probably better that way. And so, so when I thought a long time about it, I'm actually not, I'm a spectroscopist, but I'm not an atomic physicist. And so what I thought I would do, and I hope I don't insult anybody's intelligence, but sort of talk about spectroscopy theory from the perspective of how I, as a astronomical can't even pronounce it, spectroscopist, that thing up there, spectroscopist, for about 40 years. You'd think I'd learn to say the word, what's the important stuff and what's the stuff that doesn't matter. So let's go to the next one. Okay. Okay, so first of all, if you want these slides, because there's some stuff in it that it's hard to get, just email me next, because it's at this address. And if you can write that all down correctly, then you don't have to email me, because that's the download site. But saint@cfa.harvard.edu is easier to scratch down right now. Next. And you don't have to write that thing down and not make any mistakes. So, sort of the outline is that I was going to talk a little bit about history, because it's sort of interesting to know where these things came from. Just a quantum mechanics refresher. I mean, I think most of you learned some quantum mechanics, but this is, again, the things that I carry around in my mind, and I forget everything else. A little bit about atomic spectroscopy, actually more than a little, and then just a taste of spectroscopy of diatomic molecules, because molecular spectroscopy is a vast and deep ocean of information, but it's just sort of how you think about things and what the important physical processes to understand without getting drowned in that ocean. And then finally, an example or two of what spectroscopy is good for. If you're, okay, great. Fruits.
Next.
Yep, right. Okay, what spectroscopy is good for if you happen to be an astrophysicist. So, a brief history of spectroscopy. So, well, great. So Newton didn't actually invent astronomical spectroscopy. There were these guys named Kirshner, Marcy, Boyle, and Grimaldi, and probably some people that history has forgotten who invented prisms. But Newton gets the credit because his study was pretty comprehensive. I mean, he really wrote down what was going on in the solar spectrum for the first time. He couldn't do any spectroscopy, really. He could do continuum spectroscopy. But the important thing he did is, there was this question about whether a spectrum, the prism was putting colors in. The way I feel, if you have a colored light source, whether the prism would, you have to remember they didn't know anything in those days, whether it was imparting colors to the white light or whether it was just taking the white light and breaking it up into its constituent colors. Really important historical thing. And he did that mostly by showing he could take a white light from the sun, split it into colors, have another opposing prism of about the same power or refractivity, and put the white light back, put it back together and get white light. Of course, the important thing about Newton was he was very, very wrong about whether light was a particle, or maybe he's way ahead of his time, light was a particle or a wave. And the fact that he insisted on it being a particle for so long set spectroscopy back for a long time. So I think people forget about this, but Herschel did something very, very important. By the way, Herschel was very, very interested in climate change because they knew that the sun pulsated, and he was worried that pulsations of the sun would in fact affect the climate and have very hot summers and cold winters. But he was the first person who detected, let me see, does the laser work? Yeah, oh great. He's the first person who discovered invisible radiation. He discovered, wavelengths beyond the reddest. So here this is this illustration of this is the only light source they had that was bright enough. It's projecting a solar spectrum, and he put some thermometers here. This is the last red feature in the solar spectrum, and when he opened up the slit, those thermometers got hotter. So he knew that there was something there. It was infrared radiation. And so that was sort of a important step. Steps go slowly at this top point in history. So, so Wollaston finally adds a lens to Newton's spectrograph, and that sharpens up the resolution of the spectrograph. And so Wollaston determined that the solar spectrum wasn't uniform. I mean, previously, Newton had seen these sort of smooth blur of colors because a prism all by itself doesn't have enough dispersion to resolve the lines. And Wollaston didn't really resolve the lines, but he saw these bumps in the spectrum. and indicated to him that there was something going on. And then Fraunhofer was the first person to use a diffraction grating, and diffraction gratings give you much higher dispersion, and so you can see things that you can't see before. And so at higher resolution, the deep, dark Fraunhofer lines, Fraunhofer worked to around 1814, became apparent, and I think this is a reproduction of Fraunhofer's original spectrum showing the Fraunhofer features and the fact that the sun's spectral energy distribution peaks around somewhere in the yellow-green, which is an important thing too. And Kirchhoff finally showed that the spectral features could be associated with specific chemical elements, which is what this talk is all about. And this is just a picture, this is sort of better picture of the Fraunhofer spectrum and showing the prominent features. Let's see, here's the laser. There's H alpha, sodium D, anyway, as calcium H and K. I'm not sure that they actually did Fraunhofer see calcium H and K? I guess maybe he did, because it's pretty dark blue, deep blue. So anyway, so at the end of the 19th century, spectroscopy starts to explode because Röntgen discovers X-rays, which people realize is a form of light. Somewhere along the line, Maxwell has written down Maxwell's equations that showing that light is a transverse electromagnetic wave. Becquerel discovers radiation. Xamon discovers lines can be split. Larmor develops a solar system model of the atom with the electrons and with electrons going around positive protons, which he called positive electrons. Oop, sorry. Oh. That's a spoiler. So, the revolution continues in the 20th century, where light is seen to be an electromagnetic wave and a particle. Matter turns out to be particulate and a wave, so it's wave-particle duality. Bohr explains the spectrum of the hydrogen atom. That was a huge step. And then finally, I think the big closer was that Schrodinger shows that matter waves are oscillations of probability. So quantum mechanics, when you're talking about electrons and protons, material things, they are oscillations of probability. More on that later. So it's important to remind ourselves what the features of quantum mechanics are. And if it's old hat to you, I'm sorry, but I think this is a school. So, and the important thing is that they have a series of books in the United States called For Dummies. So there's calculus for dummies and Korean for dummies and Arabic for dummies. They're really good books, by the way. I bought Organic Chemistry for Dummies. If you want to learn about organic chemistry fast, it's a great way to go. But it's not that we're dummy, but we're also not physicists. This is the important thing. So we don't need to know everything physicists waste their time thinking about. We're astrophysicists, okay? And it's important to remember the difference between the two. We are consumers of things that physicists produce. So, some basic tenets of quantum theory are as I said, the wave-particle duality. And so light is a wave, but so is matter on small enough scales. So the electron, for instance, de Broglie postulated that the electron and showed that the electron also had a wave-like character. And light is a transverse electromagnetic wave, but it can also be a particle. And what matter waves are probability waves governed by a flow equation, the Schrodinger equation. Matter is particulate, but so is light, and that's shown by Einstein. Einstein, by the way, won the Nobel Prize not for any of his relativity, which actually they said when they awarded him the Nobel Prize for the photoelectric effect, which showed that photons could behave as light could behave as particles, as photons. In the recommendation, it said, despite the fact that he's got these crazy ideas of time dilation and relativity. So, the important equations you want to take away, and I think everybody knows these, are that quanta can be assigned an energy. And the energy is h nu for a photon. If you know the wavelength of an electron or a proton or something small, that works too. And the h is just the the Planck constant, which is not a very bright laser, Planck constant, which is a very small number in MKS, and nu is the frequency in per second. So in free space, the other thing is that in free space, I mean, if quanta aren't bound, they can take on any energy value. So an electron can have or a photon can have an arbitrary energy. But if you bind them, if you confine them in space, then they only have certain specific values. And I'm going to spend some time doing some toy models. You might have done them as an undergraduate, but they're good models to have in your head when we get to particular molecules. And so, and the other thing is, the other important thing, I don't really talk much about this, but it has to do with line width, how wide the lines are in a spectrum, is that nature is intrinsically uncertain. You know, it's not that you can do a better experiment and determine physical parameters. If you learn a lot about one parameter, you give up information about another parameter. And so in the Heisenberg uncertainty principle, the uncertainty stated that the uncertainty in the energy of particle and the uncertainty in the position of a particle are equal to h over 4 pi, which we like to compress to h bar over 2. H bar is h over 2 pi. It makes things more compact. But the bottom line is that if you do an exquisite experiment to measure the energy of a particle, it becomes non-localized. You don't know where it is. So here's a useful toy system to sort of illustrate a lot of the principles of quantum mechanics. I mean, that's all. I've just written down all of the quantum mechanics you really need to know, except for the Schrodinger wave equation. And so the sort of classic thing which is illustrative, and then when you expand it a little bit, becomes even more illustrative, is the infinite square well potential. And so this isn't a very imaginary thing where you have a potential, electromagnetic potential, gravitational potential, but the walls are absolutely straight and infinite. There's no way for that really to exist, but it's a good thought experiment. And so the point is that because the potential is infinite, there's zero probability that the quantum ever is outside that well. I'll amplify on that in a couple of slides. And so the thing is that we talk about the wave function, which is the thing that is in the Schrodinger equation is the flow of probability. The wave function is not actually probability, as we'll see later on. It's the wave function times its complex conjugate. But if the probability has to be zero, the wave function has to be zero too. And so that means that if we denote the wave function by phi, oh, there it goes. Here's the laser. Phi, that says that phi has to be zero in these gray areas. The wave function has to fit in here. And so the answer is pretty darn simple, right? It's just sinusoidal functions. They have to go to zero at the end, and they can be zero in the middle or arbitrary places in between. But the bottom line is it's just like the motion of a string in a stringed instrument, right? Strings, if you tie the string at both ends, you can put all kinds of not arbitrary shapes, you can put all kinds of shape, well, they can be arbitrary, in between, but the simplest solution is a sinusoidal function. What happened to my, anyway, so the solution is simply that the wave function is, the laser likes to work sometimes and not other times, is just the sign of some argument where with the arbitrary parameter n, where n could go from 1 to infinity because it's an infinite square well. And so this is a solution to the Schrodinger equation, which I won't belabor, but it's worth understanding that this is just that the the time derivative of the wave function, double the second derivative of the time equation minus the potential is equal to the energy of the system. And so what you'd like to know is this quantity E, the energy of the quantum in quanta, and I lost all these things, in all these different states. It's just this thing here. It goes as n squared. There's a typo there, because one of those should be h. Sorry about that. It's n squared, h squared, 8 mass of the particle, and the size of the well squared. And so those are if you put particles in there, that's the only energy levels they can occupy. Oh, so I made this movie. I didn't. Can we make them? There is. Oh, there we go. Yeah. Anyway, so this is sort of a funny little cartoon. So you know, in a particle view of the way this toy system, right? We have to imagine this particle bouncing back and forth because it can't go out of the well, and you know the way a rubber ball would. But in the wave view, the electron is described by a wave function that has to be 0 at the walls instead of this thing. And the probability in some way is of where you're most likely to find that electron has to do with the wave function. So the thing is the system is quantized, and the particle in both the wave and particle system can only have a specific energy level. And that's not really totally apparent in the particle view. I mean, if you only think of things in terms of particles, you're going to think that any energy is possible. Oh, okay. Oh, where was the movie? So the thing is that we've been going along pretending that the wave function is a real function. It's really not. It's usually, you know, if you're doing things right, if you're doing slightly more complicated problems, it's a complex function, okay? But everything in the real world, so you have this wave function, it's complex, it has an imaginary part. In the real world, everything has to be real, right? You have to, at the end of the day, you have to have real quantities. And the other thing you notice is that if the wave function is both positive and negative, so it's very hard to have a negative. I mean, I'm jumping ahead and assuming that this has something to do with probability. It's not possible to have a negative probability. And so the truth of the matter is that the probability is in fact the complex conjugate times the wave function itself, the modulus of the wave function. And so if you have these simple solutions like this, when you form the modulus, it's always positive and it's also always real. But we can, you know, the important thing is that these are probability functions. They don't go. What happened here? I'm having a hard time. These are you never localize the particle. You just say that the particle in the box is. If I was going to look for it, I'd look for it there because that's the likely place. I probably wouldn't look for there, and I certainly wouldn't look there. But it could be right there. Okay, so. Okay. So the question is that you have these different energy levels, and in this toy system, and you would like to move the quantum from one level to another level. I mean, there are many physical processes that can do this. If another electron came in and hit it, that's possible. But in spectroscopy, we're interested in transitions that are induced by the absorption of photons, okay? So spectroscopy, we assume that the way the quantum, if it was in the n equals 1 state, gets to the n equals 3 state, is because a photon comes in and hits it and adds energy to it. And then if it's in this upper state, they're not stable. This is not a happy place to be. And so the electron, if this was an atom, would take, in about 10 to the minus 10 seconds, would drop back down to either cascade. I mean, so it's possible in this system for the electron to go from here to here to here to here, or from here to here. Those are details. But the important thing is that you will only get this electron to move from, or quantum, from here to here if the photon has exactly the right energy, which is the difference of the n=1 state and the n=3 state. And when it drops back down again, of course, it will emit a photon, and it will have exactly the same energy. It's just one energy. If it's off by a little bit, it won't happen. So the thing is now, to sort of explore a little further, we say, well, let's not make the well infinite. We say that this is more something closer to reality and something you might actually use as a model. And so now this has some finite potential. And the important thing is that all of a sudden there is a finite probability of finding the quantum outside the potential well, which doesn't happen in reality. You know, the old picture of a ball bouncing back in this back and forth in the box, the ball never never exceeds the boundaries of the potential well. But now that it's finite, now that it's finite, in fact, you can have leakage outside the wall. And it turns out that if the wall, if instead of being continuous is this very skinny wall, then even though you have a potential this high, a quantum with energy this low can, if it's thin enough, sneak through, and that's quantum tunneling. But when it gets outside the box, it decays pretty rapidly to zero, as something like e to the minus x, where x is the amount you're extending out of the box. Now the other thing is the shallower the well is, the further the quanta can penetrate into the walls. It's sort of like the cage gets softer. And the net effect for the principal quantum number is that because now the wavelengths are a little bit longer than the infinite potential well, the wavelengths, you have longer wavelengths, which means lower energies, because E equals H, as lambda gets larger, the wavelength gets larger, the frequency gets smaller, and so E equals H nu gets smaller too. And so, let's see. Well, here's in fact a kind of interesting thing about quantum tunneling. This illustrates actually an astrophysical concept, and that is that it turns out that, of course, we all know that the primary source of solar energy is the PP cycle, where two protons fuse and release energy. It's a fairly complicated cycle, but that's how it starts. And the truth of the matter is that because the protons are, when they get close together, become slightly positively charged, have a potential barrier. They don't want to, And if you calculate the mean thermal energy of protons at the core of the sun, they have much lower energies. So if it wasn't for quantum tunnel, but the thing is that it turns out there's just enough quantum tunneling so that even though the potential barrier is higher than the actual potential barrier is higher than the sort of mean kinetic energy of the protons, quantum tunneling saves the day. The sun comes up every morning and the Earth is warm, because without quantum tunneling, the sun wouldn't work. Let's see, just some sort of terminology and some boundaries on what I want to talk about. For spectroscopy, we mean for me, when I'm talking about it, I'm talking about infrared, optical, and UV electromagnetic radiation. There are lots of different kinds of spectroscopy. It's a huge, huge subject. They have a meeting in the United States every year. Thousands of people come. There are acousticians who study sound spectroscopy of sound, particle physics, where the accelerators like the CERN LHC talk about things in spectroscopic terms, gamma rays, X-rays, and radio wavelengths all operate, do fascinating things, and I mentioned an example at the end, spectroscopically. But the fact is that although they talk about X-ray spectroscopy and gamma ray spectroscopy, light is behaving very much like a photon in that regime. It's very much particulate. So, in fact, what I really am mostly interested in for the purposes of this talk is spectroscopy you can do from ground-based telescopes, which means near infrared and optical. And I'm not going to discuss radio. What else? And so we're mostly discussing atomic, so we're mostly talking about atomic transitions and molecular transitions, and mostly bound systems. I mean, there's all kinds of emission spectra, Auger spectroscopy. It's a whole different subject. And then there's just this truism, I think I've said it before. And one other thing about spectroscopy is physicists and astronomers don't speak the same language. Physicists love to talk about things in terms of frequency and inverse wavelength. And astronomers prefer angstroms, nanometers, and microns and nanometers and angstroms. And this causes endless confusion because I can never look at an atomic physics paper because it's all I'm sitting there and I'm trying to go, let's see, 1 inverse at 10,000 inverse centimeters. Anyway, so we live in the world of wavelength, not frequency. So, you know, sort of the starting point of spectroscopy is Bohr's hydrogen atom. And that actually starts out with the insight that all classical properties, that, you know, angular momentum, momentum, energy, all have quantum analogs. Although things get sort of funny on quantum scales. And, you know, de Broglie first showed that matter has a wavelength that's related to its momentum. And so the wavelength is equal to the momentum divided, 8 Planck's constant divided by the momentum. And so Bohr imagined the wavelengths of an electron sort of wrapping around the nucleus. And from a sort of really primitive point of view, it's just if the wavelength wasn't exactly right, as the electron spun around many, many, many times, it would destructively interfere with itself and go away, which is kind of a bold thing to think in those days. And so he imagined that the line structure corresponded to different principal quantum numbers where the wavelength just, you know, was exactly a perfect fit to the orbital radius. And so each orbital had a principal quantum number. Oh, there we go. Ooh. And the amount of energy that was needed to be absorbed or emitted, it needed to be absorbed to move to a higher quantum level or drop down from a higher quantum level to a lower quantum level was given by this equation where this is the Rydberg constant, which I'm not supplying here, but you can look up in any book. So that's the quantum setting. So atomic spectroscopy. Well, we're going to start out talking about hydrogen because it's the simplest element and it's sort of the poster child for the rest of spectroscopy. Turns out to be just sort of embroidery, mostly embroidery, although there's some things that start to happen in atoms that are not hydrogen-like that are sort of interesting. So one thing you can do is there's sort of 2 forms of spectra that we talk about in astronomy, well, in spectroscopy, and that is if you add energy to a gas, for instance, that a classic way to do that is a discharge lamp. So you have a very high energy electrode here and here, and if the gas is at the right pressure, the gas will start to ionize, and then it will start to go to the other electrode and collide with other atoms. And as it collides with other atoms, it will turn them into ions. And then the electrons will be also furiously recombining with the protons that are sort of sitting off to the side. And what you do is you get what we call an emission spectrum. So it looks something like this. And the kind of neat thing about hydrogen is it doesn't have a particularly rich spectrum. It's not very confusing, and you can really tell what's going on. And so the classic way to study this would be to have an emission lamp, a lens to focus your light onto a very narrow slit, then take that and collimate it, image that slit, take that slit, and after putting it through a prism, image it onto a photographic plate or a screen or a charge coupled device or some kind of electronic thing. Now, the other alternative is what we call absorption spectra. And so if you have a light source and then a bottle of some kind of gas, and it can be, you know, when we're talking about stars, it can be, iron can be a gas, okay? So it's not, we're not just talking about the gases we know on Earth. But anyway, you pass the white light through the gas, and then you disperse it. This is just shown schematically as a prism. No modern spectroscopist would use a prism. We'd use a diffraction grating, and then project it onto a screen. You'll see these dark bands. Again, these are the Fraunhofer spectral features, and they're exactly the same as the emission features, except, this thing's dangerous. They're at exactly the same place. It's just at one point the absorption features are filters filtering out specific wavelengths. In the other case, you are actually making light in the features. So situations like, well, let me go on. So I'll show you an example. So this just sort of, when we talk about spectra, they sort of break into three categories. They're continuous spectra. I mean, there's some things that have no line structure. An incandescent light, you know, the old kind of light bulb that you screwed into the wall. It has no absorption or emission features. It looks like this. If you have a hot gas, something like a planetary nebula, an active galactic nucleus, you're going to see an emission spectrum. So, but you will always see sort of this faint continuous spectrum in the background in any real astronomical spectrum. And then finally, if there's some cold gas and a light source, where cold is sort of a relative term, when we're talking about stars, 2,000 degrees is cold, then you get an absorption spectra, and behind the absorption spectrum, you see the continuum. And I won't talk about this, but my wife is a very hardcore spectroscopist, and one of the really hardest things when you have lots and lots of absorption features is trying to figure out what that continuum is. Turns out to be more an art than a science. Where am I in time? I've lost track of it. I'll keep going. So, you know, here's a classical case of an absorption spectrum, and it's what stellar spectroscopists do all the time. And I told you before that when you're doing absorption spectra, you have a light source, and then you have a box of gas, and then you project it onto a screen. Well, here in this example, you never do this, but the screen is your eyeball, but it could be a spectrograph. And so the continuum light source is sort of this, the interior of the sun is fairly opaque, and the propagation time of a photon from the center getting out of the sun is, I think it's 500 minutes or something. I don't know that number exactly. But anyway, so the thing is you have this continuous light source at the top of the convection zone, and that's about 5,800 degrees Kelvin, which is it's yellow-green, that's the color temperature. And that determines the color of the sun. And it passes through the top of the upper levels of the photosphere and the chromosphere. And in the process, in fact, that stuff. I mean, when I said it was cold gas, it's 4,500 degrees, but nonetheless, it is considered cold to a spectroscopist, and it produces these absorption features. And so, okay. Oh, absorption feature. So, you know, this is classical stellar spectroscopy, and there are many, many details to this. It would take 2 or 3 semesters to go over all of it. But this is sort of the general principle of stellar spectrum, and a lot of other spectroscopy we do. Now, the one thing is that, you know, the Bohr model is very, very cute. It's, you know, the idea that electrons, you know, sort of going around like the planets in the solar system is very attractive, and it's kind of a good toy model. But the truth of the matter is, that's not the truth at all. You know, wave functions are described by extremely complicated equations, and so the solution for the hydrogen atom is this big terrible thing that has spherical harmonics in it, and these are Laguerre polynomials, and these things are a mess to calculate. But nonetheless, we can look at the pictures of them, and so the n equals 1 orbitals look something like this. The n equal 2 orbital looks like this. But wait a second, it looks like this, and it also looks like this. And the thing is that we're going to discover in a second is that not only is the energy level quantized, but so is the angular momentum. And there's some rules around that. And so this is even, they're really beautiful pictures, but as you go to n equals, beyond n equals 2 to n equals 3, up at n equals 4, things get terribly complicated. And I leave it to my physical colleagues. But again, it's this very complicated equation. But if you plot it in 3 space, this is what it looks like, or at least 2 space. So this is, the reason I put this in, this is mislabeled, I'm sorry. The important thing to realize is that we do all these things in, if you ever want to encounter, you know, engage with this equation, the thing is that this equation is cast in terms of spherical coordinates. And so that's right. This is just, so when you go and you want to calculate the wave function, I don't know why you'd want to, but you could. If you want to calculate the wave function, you've got this r. Well, you've got this r here, and you've got this rho. Well, rho. You should have a theta and a phi, and that's because this is all done in spherical coordinates, where rho in this case is the radial distance from the center of the coordinate system, the nucleus. Phi is the polar angle, and then theta, it's kind of obvious, opposite to how I usually annotate it, but theta in this drawing is in fact the azimuthal angle, the angle around the axis perpendicular to the z-axis. Just an arbitrary thing. But. So anyway, hydrogen spectral series, they're actually organized by the name of their discoverers, so that they're for transitions between n equals 1, principal quantum number 1, to higher quantum levels, or Lyman series, I don't know his first name, and then the Balmer series, which for an optical astronomer, which are mostly optical lines, that's n equals 2, and their Paschen and bracket are mostly infrared lines. You can see over here that by the time you see the Lyman series is mostly, it's all actually ultraviolet. The Balmer series, H alpha is one of the most famous lines, in the red at 65, 63, and then there's Balmer beta, gamma, and delta and gamma, and those are all visible wavelengths. Okay, yeah, as I said over there. So the trouble with hydrogen is that it masks the complexity that you've seen in more complicated atoms, especially the issue of angular momentum. Because like energy, as I said, any classical mechanical quantity can be quantized, has to be quantized. And so the fact that the electron it's not going around in a circle, but there are some of those orbitals that tend to circulate more like a planet, and some of them that don't. And so the you can attribute an angular momentum to that, and that angular momentum is quantized, and it's indicated. This is an unfortunate font because you can't tell 1 from an L, but that's supposed to by the quantum number L. But the thing is that the effective angular momentum only becomes apparent if the atom is slightly more complicated than hydrogen. Now, when I say that 1 electron, it is in fact, well, here, let me put this up. 1 electron, people who work in, for instance, X-ray astronomy talk about hydrogen like xenon. Not xenon, but hydrogen like neon. Because in X-ray astronomy, processes are so energetic that you can in fact have all the electrons but 1 stripped off. And so that you've got a neon nucleus with 1 electron. It's a very, very unusual, I mean, from my perspective, unusual. My wife, who's an X-ray spectroscopist, loves that stuff because all you have to do is use the Bohr atom to describe it. You don't have to worry about all the other different couplings. But anyway, the thing is that you can write the energy level diagram for the Bohr atom, the hydrogen atom, without really recourse to any complexity. It's really just a question of, what's the starting quantum level and what's the finishing quantum level, and you're done. And that makes life pretty easy. But the thing is that hidden behind all of this is that there's angular momentum too. So it turns out that the n equals 1 state, somewhere along, let me just jump up. You'll see at the top of this chart things are called SPDF, and that has to do with the fact that spectroscopy is an old science, and people name things in funny ways. So, sorry, put this chart farther back. But they label, in the good old days, which were the bad old days, they labeled the angular momentum states by SPD, which stood for sharp, principal, diffuse, and that should be an F, fundamental. Sorry about the typo. But this column here are all the angular momentum 0 states. These are all of the angular momentum 1 states, angular momentum 2, and angular momentum 3. And I'll get to in a second, there's a hierarchy that you can only have a certain number of angular momentum states for a given principal quantum number. And so, but the bottom line is that you see a little complexity here, and that only certain transitions are allowed. But in the Bohr atom, this S state and P state have exactly the same energy, which isn't true for any other atom. And so, one thing that makes things, one added complexity that's sort of hidden back there and the physical import of this won't come on, is that not only do you have an angular momentum, that should be an M, but the thing is, it turns out that if you pick a direction in space, and usually this happens when you take an atom and you put it in a magnetic field, and atoms behave like compasses, and it'll go, and it'll align away in a way to align itself with its magnetic moment. They have magnetic moments. And now this defines a special direction in space, which we call the z-axis. It's just what physicists have been doing for 120 years. This is the z-axis. And so what is not only quantized, the angular momentum isn't just quantized, so is the projection of the angular momentum onto this z-axis. So if you can imagine one angular momentum state orbiting like this, and this is again a toy way to view it, and one like this, that you're only allowed to have those states where these are quantized as h bars. So there's an mz equals 0 state, and mz equals 1, and an mz equal 2. And the thing is, let's see, you're right. And the magnitude of that, I apologize, that's a typo. That should be an m. So the magnitude of that arrow is then h bar times mz plus 1. So let's see. So, as I was saying before, you look at the Grotrian diagrams, and the Grotrian diagram is sort of a handy thing because these are the principal quantum numbers, these are the angular momentum states. It kind of lets you, it gives you a fairly simple way to encode what's possible within the atom. And so we see that there are some states that they're arrows, and that means that they're what we call allowed states, and that means those transitions can happen fairly frequently. It is possible the states, some levels you sort of get stuck, and there's no place to go. So there are no arrows that go from the n equals to 0 angular momentum state, because that's not allowed. I'll get ahead of myself a little bit, and of course the rules are that you have to change the angular momentum quantum number, angular momentum quantum number by 1. So if you're going to transition from this state to this state, you have to go this way or that way, but you can't go that way because that's a delta L of 0. You can, in fact, have forbidden transitions, but they go very, very slowly compared to the allowed transitions. And so unless an atom gets stuck in this state here, the atoms get stuck. And that's how lasers work, because what you do is, it turns out that all of the rules I'm telling you go out the window if instead of a photon hitting it, another electron hits it, or another atom hits it. If another atom hits it, all of the spectroscopic stuff I told you isn't true anymore, and any transition is available. So what happens, of course, is in a laser, you create populations where you fill up these dead-end states that nothing can get out of, and then you have stimulated emission where you violate all these rules, and so you get a whole bunch of electrons in that upper state, and then you let them all go at once, like opening a sluice in a dam. Let's see. So as I just said, if energy is carried away by some other means than radiative transmission, like the spectroscope, radiative processes are what we study in spectroscopy, anything's possible. So we're just studying radiative processes here, and I say, and they do have, the forbidden transitions happen, but really, really slowly. So the rule here is, as I said before, you have to have a transition that not only changes principal quantum number, but it has to change exactly an angular momentum quantum of 1. And that's because the stimulation or the excitation or de-excitation of the atom is radiative process is carried by a photon. And photons are spin 1 particles. So when the photon takes away 1 quantum of spin from the atom, or adds 1 quantum, then the angular momentum of the orbital changes by 1 h bar. So that's a statement of conservation. So spin angular momentum must be conserved if the photon carries away or adds 1 quantum of angular momentum. Now the last wrinkle in all of this is you have principal quantum number, and then you can have angular momentum, and each angular momentum state can have their different m states. But then it's possible, there's another issue about how many electrons you could put into each of one of those states. And so electrons are fermions. They're spin 1/2, and so they plus or minus 1/2. And so the Pauli exclusion principle says you can't have any two electrons in the same quantum state. So an orbital is a quantum state, and so if you put one electron in, which got a spin minus 1/2, you can put another electron in that has spin plus 1/2 because they have different quantum numbers, but that's it, because there are no other spins. And so you can't put in two electrons that, for instance, have both spin minus 1. And so as you fill the orbitals up, you put them in, you sort of put them in two at a time. So the simplest case is the n equals 1, which only has one angular momentum state, which means it only has one m number, and so you can, the quantum state is entirely defined, so you can put in exactly two electrons, one spin up and one spin down. And there's this kind of handy diagram that shows you how to calculate what orbitals fill. So when you get to complicated atoms that get up to very, when you put two electrons in here, it's full. So then the next electron has to go in the 2s state, and you can put one more electron in here, but then that's full. Now you put it into the 2p state. The 2p state, in fact, has 3 L quantum numbers, and so you can put in, there are 3 different quantum states, so you can put in 2 electrons for each, so there's 6 of them in here. And the only thing is when you get to fairly high quantum numbers, let's see, 3. Where is 4 or 5? Anyway, so this is sort of a handy way to figure out, you put in the right number, you put 2 electrons in this column, 6 electrons in this column, and 10 electrons in this column, so that, 2, 2, 6, 2, 6, 2, 10, 6, 2, and that's how you build up the periodic table. So, one thing is that atoms don't have to be in their ground state. I mean, if you have if a 103 nanometer photon hits a hydrogen atom in its ground state, the electron will jump up to the n equals 3 state, which is here. And it'll probably back down to n1 for what these are called dipole transitions, allowed transitions. It'll probably drop back down in the usual figure of merit is 10 to the minus 10 seconds. And then if it gets hit by a longer wavelength photon, if it's the right wavelength, it'll go to the n equals 5 state. So this is a short amount of time, but if you have enough photons hitting atoms all the time, and there are a lot of photons, for instance, the photosphere of the sun and the chromosphere of the sun, there'll be a fair number of particles a fair number of atoms that are actually in these states up here when you look at the spectrum. What part of what makes stellar spectra so difficult? So I think I sort of said this before. So, go on. So there's one important thing, and that is I've been talking about the orbitals as if they're independent. They're different racetracks, and little cars, horses are running around the racetrack, and then they hop into another track and go around in the Bohr model. But the truth of the matter is that what you really care about are the quantum states of the whole atom. And so when you look at the literature on atomic physics, if you're studying you find a peculiar line in a spectrum of a star you're observing, and you want to look at its Grotrian diagram, which tells you what all the energy levels is, and you're trying to find the energy level that corresponds to the line you detected. They're not going to talk about SPD. Sorry about that. They're not going to talk about SPD. They're going to talk about capital letter SPD, and that SPD refers to the state of the whole atom. And so the lowercase letters, and so the capital letters generally are talking about the angular momentum of the outermost electron, because that's the one that matters. And the subscript, so if you look at this up here, there's 1 SO, 1 0, 1 P, 1 D2. And so the thing is that this substrate tells you the total angular momentum of the atom. This tells you the excitation state of the outermost electron. And this tells you, forgot right this minute. And so the other thing is the hydrogen atom is kind of nice and simple, but it masks the fact that in a real atom, a complicated atom, the hydrogen atom, all of the angular momentum states are absolutely same energy. Not quite, I lied, but almost. You have to work very, very hard to tell the difference. But if you look at a calcium atom, which has 20 electrons, there's a high level of complexity in the levels, and the different angular momenta have different energies, and that has to do with a bunch of interactions within the atom, some of which are not so obvious at first. When you first start thinking about it, so if you look, for instance, at the n equals 3 level, you can see that these angular momentum states have very different energies. And it has to do with a number of things. But the thing that's kind of cute, I stuck this in, is of course you can look at the periodic table. This is how we chemists would look at the periodic table. It's, it tells you the atomic mass and all that other useless information to an astronomer. But this one is a really great one. This is the spectroscopic periodic table of elements, where these are emission spectra. But if you can buy big posters of this, and it's not quite so good on the screen, but if you got to find a really good poster of it, and you really start looking at how all the different elements have all these different features that are sort of neat, and it underscores how different the different spectra are. The spectra where the elements that don't have many electrons, don't have many lines, and then you get to heavier and heavier and heavier things. Thorium is the one that I use. Where is thorium? Where is thorium hard? There, thorium. That has zillions, and uranium has zillions of lines. The more electrons there are, the more lines there are. It's also sort of interesting that in the middle of the periodic table, the elements seem to have more lines than the edges. Anyway, the bottom line is this: with that periodic table, this is a solar spectrum, and what's been done here, this is what we call a shell spectrum, and it's a tricky instrument. I spent the last 30 years building them, and so what's happened here is that there's a very, very high dispersion, high resolution diffraction grating that disperses things from, it's hard to tell in this, it goes from blue to red. So this end is a little bluer than this end. But then in the instrument you have a weak dispersing element, a prism, and it spreads the light out gently this way, so that otherwise if you didn't have what we call a cross disperser, all of these lines would lie on top of each other, and you would have no useful information. So this sort of spreads the whole thing out and makes this glorious map. And so you can identify some of these things just on inspection. The Fraunhofer line I told you about, which is sodium in the photosphere of the sun, are these two lines here. It's a very famous doublet. And then down here, these big wide lines here and here are calcium H and K, which are huge, huge absorption features. And there are lots of other things. Some of that, I believe, is hydrogen beta, which I talked about before. Anyway, you spend a lot of time staring at this and looking at the atlas, figuring out what they are. So anyway, the thing is that in simple atoms, in simple complicated atoms, the in a hydrogen atom, the quantum number, a 2s and a 2p angular momentum state have the same energy. But the thing is that when you actually put in relativistic theory, I didn't very much. When you put in relativistic effects, you actually, even in hydrogen, but not very much, start to split the angular momentum 0 and the angular momentum 1 state. But then when you put in spin orbit interactions, which are, I guess I'm done. Oh, there we go. Yes. No, fine. Then the spin, which is interactions between the spin of the electron and the orbital angular momentum, actually split things up a lot. So they actually split up the different quantum levels of the angular momentum state, and they become well separated. And those are the primary effects that cause the different angular momentum states to have different energies in complicated atoms. You can't have a spin orbit interaction in a one electron atom. There is a thing called hyperfine splitting. I'll just mention it. So over here you have fine structure, which separates things out fairly widely, but then you actually see that the states get split according to the spin of the electron, and that has to do with the interaction of the magnetic moment of the electron. The nucleus has a magnetic moment. Electron has a magnetic moment. So if the magnetic moments are like this, you have one energy level, and if they're like that, you have a different energy level. In astronomy, I just mentioned this because it's in all the books. It is called hyperfine because it's very small, and you have to work very hard in the laboratory to measure it. And so, to my knowledge, hyperfine splitting has never been used in astronomy. Well, no, but I lie because, but I'm not talking about optical near infrared. It turns out that the only way to detect hydrogen in the neutral hydrogen is the 21 centimeter Hyperfine line, and this actually arises from a different phenomenon. It has to do with the hydrogen actually always being in a diatomic molecule, and whether the spins of the total atoms, the two joined atoms, are like this or like this. But it's also called the Hyperfine line. And so this is the only, for neutral hydrogen, I mean, the thing is that when I've been talking about all of these different, Balmer series and things, for part of the time, it's it's very excited. The cold gas in the universe never gets excited. So this allows you to, at the radio 21 centimeters is very, very deep into the radio, but you can make these gorgeous maps of neutral hydrogen in the Milky Way and beyond the Milky Way. And if you're a keen observer, you can see these two little dots down here, and those are the Magellanic Clouds, which also have. And so one of the early detailed mappers of 21 centimeter radiation was the Very Large Array in New Mexico, which is an array, so it got very fine spatial scale. So one thing that is interesting, a splitting phenomenon, is the Xamon Effect. And so it turns out if you take an atom that has a angular momentum that allows multiple M states, so for instance, P state at J equals 1 state can have a M equals 0, 1, and minus 1, and a state. And so that, I told you before that has to do with the alignment of the Z component of the orbital. And so the thing is that depending on the Z component of the angular momentum, you'll get different interactions with an external magnetic field, and then the levels will start to split. And so, for instance, L equals 1 will produce 3 lines. And the thing that's kind of neat is that the amount of splitting is going to depend on how strong the magnetic field is. So this is, can't read my own writing here, but rubidium is something that people love to work with for this sort of stuff. So the Xamon effect is stronger in some elements than others, depending on the electronic structure. But the thing is that as you take the magnetic field and start to turn it up, here they plotted the frequency shift, but remember E equals h nu. So with the right algebra, you can turn this into an energy. You actually see these different M states start to spread out. So the point is if you know the element, and so you know what M states you're looking at, you can actually use this to measure the strength of the magnetic field. So this is just some more pictures of how this works. So, you have this J state, but as you put in as you turn up the magnetic field, the M states all have separate energy levels. And so this is just, again, this is physicists using frequency instead of wavelength, but this is just showing turning on a field. It does it in pieces of Gauss, not very strong field. So here you see 1.8, 1.36 Gauss going up. And anyway, as I said before, so when you put the atom in a magnetic field, it's like a compass. It points its needle along the magnetic field. That defines the direction of all of the M states, and the amplitude of the M state determines what the energy is. So this is pretty cool stuff. A classical example of this is, for instance, you can use it to measure the strength of magnetic field in sun. So the quiet sun has a magnetic field, but it's modest. But then in sunspots, the magnetic field is quite strong. And then, of course, the sun exhibits these enormous flares. You can't really read this, but this is a flare, and that's the size of the whole planet Earth. These flares are very, very big. And the magnetic fields what's going on in this flare is a whole bunch of charged particles are being spat out, very hot charged particles are being spat out of the sun, and there's a magnetic field that comes out. This is the North Pole, and it connects to the south pole. So these are all ionized particles, so they have charge, and so they travel on Larmor orbits where they go corkscrew. They go on a path like this, but they follow the magnetic field, and so you see this bright stuff. But if you do Xamon measurements of those things, you can actually then measure pretty accurately what the magnetic field of all these different things are. And the spots you can see can be really quite large. I think this may be the biggest spot that was ever detected in modern times. The kind of interesting thing is this isn't just the sun, even though stars, we resolve the sun, so we can tell, where there's a spot and where there's no spot. When you look at another planet, another star, some arbitrary star, except for Betelgeuse, which you marginally resolve. You never resolve a star. It's just this little dot of light. But it turns out that they use very complicated deconvolution schemes that are like magnetic resonance imaging that they use in medicine, so that if they look at the time sequence of just how strong the magnetic field is, so they measure the Xamon splitting of the light from the star, they can actually make a pretty accurate map of what the spots on the star look like. So this is a very powerful technique. So I was going to talk a little bit about diatomic molecules. Before I get going, I have to say that atomic physics always seemed very complicated to me, but I started learning about molecules about 10 years ago for various reasons, mostly having to do with being interested in looking for life on planets beyond the solar system, which I'll talk about on Tuesday, I guess. It's just vast. I mean, I have colleagues that did their thesis on the calculation of one state in one molecule, a whole doctoral thesis. And there are some truly amazing databases out there, but we know a lot less than we don't know a lot more than we do know. And so it's a fascinating field. So I just thought I'd talk, but there's some sort of basic fundamental processes that help you think about these things and help you, when you're looking at papers, interpret what's going on. And but there's certainly more than I could possibly present in this amount of time. So why am I only talking about diatomic molecules? Diatomic molecules consist of two atoms that are joined. And so one thing is that they're simple. It's sort of, I started out talking about the infinite square well, and you make it more and more and more complicated until it starts to approach reality. The thing is, there are, in the Earth's atmosphere, there's so many modestly more complicated molecules, carbon dioxide, water. These are pretty simple, but they already, I'll show you a little bit, already represent challenges and become complex. And then, of course, there are many very interesting molecules. DNA has zillions and zillions and zillions of atoms, adenosine triphosphate. These are sort of nice symmetrical structures. This turns into a nightmare and a horror. But so we'll just start out with the simple stuff, and I'll tell you a little bit about these slightly more complicated things, and you have to go and get another PhD if you want to learn much about that. So the other issue is why diatomic molecules? Well, the Earth's atmosphere is mostly N2, which is diatomic, 78%, and 99. It's about 21%, and so that's about 99% of the Earth's atmosphere is these two diatomic molecules. So the truth of the matter is that if you believe that the Earth is a model for, come on, man, there we go. The Earth is a model for other planets that host bioactivity, it's probably not, it may not be right, but we're the only planet in the solar system we know, in the universe we know that has life. It's what physicists call the principle of the lamppost, that you lost your keys and you go look under the lamppost because there's light there, not because you think you lost them there. Anyway. So it's as I said, it's a vast subject. It's not, and it's not just gas-phase spectroscopy. There's liquid molecular spectroscopy, solid phase, but you know, I always start out with the simplest system. So the two things I talk about. Some detail about vibrational molecular spectroscopy because that's easier to motivate. And then I will wave my hands a little bit around the idea of rotational molecular spectroscopy and then tie them together at the end. So a very good model for a diatomic molecule is just a simple harmonic oscillator. There's two masses that are tied together with some spring, and they have some equilibrium distance, XO, and there's some force that holds them together. You know, it's complicated, and I will talk about that in some detail. But we don't, right now it's not a spring constant, it's not F equals KX. But in a simple harmonic oscillator, the force is Kx. F is equal to K delta modulus of delta X, where if you try and stretch the simple harmonic oscillator away from its equilibrium position at X0, there's a restoring force that wants to push it back together. And then the potential well is 1/2 Kx squared, where the K is the spring constant of that spring. So we can start by, you know, one thing to do is always start with the simplest thing and see how well it works. And so if you, I'll just put it up here. If you have a simple harmonic oscillator potential, this quadratic potential, it's finite so that you have the wave functions leaking out the sides. It turns out that the wave function is not quite as bad as I'm just writing it down. You can go and look in some quantum mechanics books and see how you get this answer. But for quantum mechanics, it's a pretty simple answer, where it's this, all based on this thing called a Hermite polynomial. You can calculate Hermite polynomials if you want to. I would prefer to look them up. But then the energy, it turns out that when you get all done, the thing you're really interested in are what are the energy levels, and they're just h bar omega times the principal quantum number plus 1/2. Very easy. So it's your friend. And the only thing is that when we ask ourselves how well does this toy model work, there's sort of 3 different modes of oscillation, I guess. Although the last thing isn't really an oscillation. And that is when the oscillations are fairly small, any function for small amplitudes is linear, right? So for small oscillations, the spring model, which is a linear, it's a F equals Kx, it's linear, should work at least reasonably well. It seems unlikely that unless little springs, that's not even really true, because at some point springs stop behaving as linear systems. But as the amplitude gets big enough, it'll start to get anharmonic. And of course, if you put in too much energy, the spring bakes and the thing dissociates. But the thing is that there is some minimum energy to, which is an important parameter of all these models. When you put in just enough energy to break the spring, that's the dissociation energy, and that's a parameter of models of diatomic molecules. So the point is that even today, we really don't know what the right potential model is. We work with something called the Morse potential. It's not too horrifying equation, but it turns out to be slightly horrifying. when you actually get down into details. And so it's just this quantity dE and 1 minus e to the minus beta, and then delta x is the size of the departure from the equilibrium position. And so dE is, that's why the dissociation energy is important. That's dE. And then beta is some quantity which is different for each molecule, and it determines how wide the potential well is. But you can actually calculate beta if you feel like it, and so it's this equation applies, where this is the dissociation frequency. What is the dissociation frequency? Well, it's just E equals h nu, where you put in, if you know this dissociation energy, dE is equal to h dissociation frequency. So everything depends on the dissociation energy. That's just what these other things are. One other thing is that for N2 and O2 are symmetric diatomic molecules, but you can have diatomic molecules that aren't symmetric. You know, you can have CO, for instance, and so when I say it's asymmetric, I mean that the mass of one of the atoms is different than the mass of the other atom. But if it's an asymmetric molecule, you don't actually use the mass, you use the reduced mass. And so what we do is we measure D sub E and WE, and then to calculate beta. And actually getting that right is a fertile area of research for molecular physicists. So the question is how well does the harmonic model do? So here we plot in blue the Morse potential, and up here is the dissociation energy. I mean, one obvious problem with the harmonic model is it has no dissociation energy. And we see that down, as I predicted, okay, so at low principal quantum numbers, they match pretty well. And they match pretty well because they're, you know, the excursions, the amount the spring stretches isn't very big. So whenever it's a small departure, so you get a pretty good match. But up here, this is some arbitrary molecule, as you get up to even principal quantum number 2, things start to fall apart. And of course, as you go higher and higher, things get worse and worse and worse. So the thing is you could use, you'd have to go, you know, you have to, for your molecule, you have to see what this potential looks like. But if you wanted to do something easy, and you were talking about these low quantum numbers, you probably could get away with modeling, considering it to be a harmonic potential. The thing is of course, that as the Morse potentials, as you go up in energy, the Morse potentials are wider, right, because it's a fatter thing, and so then the simple harmonic oscillator, and so the energy levels are lower at a given energy level, so that this is down here again, the first, even to the 5th quantum state in this particular calculation, to the 5th principal quantum number, they match pretty well. But then when you get up to really high levels, you see that the green is the simple harmonic oscillator and the blue is the Morse potential. They're really pretty far apart. So if you download these slides, I put in one problem you could do. If you feel like doing an exercise to see whether you've understood all this, this is a problem that one could contemplate doing while you're having your morning coffee. But the thing is that it turns out that even though the Morse potential is fairly simple, it is not actually, if you put it into the Schrodinger equation, you don't get a closed form solution. So in terms of the Schrodinger equation, finding a wave function, it's unsolvable. So what one generally does, whenever you have an unsolvable problem, you take, in this case, a potential, and you do a series expansion. And if you're feeling brave, you may go to a quadratic expansion. Many times that turns out to be too hard to do, so then you go to a first order expression. In this case, they considered going to, it's not shown here, it's a third order polynomial, which consists of 1 over 3 factorial, the second derivative of the potential with respect to x, evaluated at x, and then x minus x0 cubed. And so this compares the Morse potential with the harmonic oscillator and a third order polynomial. Third order polynomial works pretty well. But obviously, as you get to higher and higher principal quantum numbers, it doesn't work so well. And so, you know, this illustrates why theoretical molecular physics is so hard. You start out not knowing that the Morse potential is a good approximation, but probably not right. And then you go and you say, well, but I can't actually even solve that thing. So what I have to do is I have to do a series expansion, and even that's an approximation. So the actual calculation of energy levels in molecules is a very fine art, which I have many friends who do, but I do not. So I don't know, maybe I can make this here. So to illustrate the, you know, the complexity of, the thing is that, okay, great. Yeah, right. So yeah, if you could just do this. If you, just for a second to see how much more complicated even a simple, I mean, this could be a water molecule. And, you know, look at all the different modes it's got. So it's got this, you know, this sort of this, Zumba class thing, this fist pumping thing, this, I don't know. Anyway, pressing iron, doing jumping jacks, and dancing on Saturday night. So when you know, even, you know, a water molecule is just one step more complicated than a diatomic molecule. And all of these different modes have different energy, different potentials associated with them. So it was a cute movie, anyway. Oh, hey, I can make it go too. But now I can't advance my slide. Oh, there we go. But, come on, let's go back. Ah, no. Okay, good. But the truth of the matter is that, I'm sorry, these are just other illustrations of the same thing. So, as I say, when you calculate to sort of summarize what I've been saying, the energy of each quantum level is this pretty simple equation. I is the moment of inertia, which is just the moment of inertia is the average position, the average mass of the, it's the first moment of the mass of the molecule. And then mu is we've got to remember to use the reduced mass, and that stuff has to go in up here. So, so the thing is that, you know, sort of comparing these things, the classical energy levels of a molecule would just be 1/2 I omega squared, where omega is the vibration rate, and I is the moment of inertia. I assume everybody knows what a moment of inertia is. But then when you quantize those things, which is not too hard to do the math, you end up with these energies, these quantized energy levels. And it makes a much tidier equation to just call these, usually in the literature, you say that the rotational energy levels are Bj, j plus 1, where you've just taken h bar squared over 2 pi and squished it together. This is what this is what you'll see in molecular spectroscopy books. And so, since again, photons are spin 1, you either add or subtract 1 quantum of spin, and so the delta J's are plus or minus 1. And only 1. Now, the thing is that you, in the even in the laboratory, it's very, very hard to isolate pure rotation and pure vibration. Usually when you excite one, you start to excite the other one. And so the transitions then are because the selection rules are combinations of rotation. So when you transition, when you have a transition, excitation or de-excitation, it's usually a combination of both. Usually a combination of both a rotational and vibrational mode. And the thing is that typically the rotational modes, these differences are typically very low energy. There's not a very big energy difference. And so they're often in the microwave. The vibrational modes can either be in the near infrared, but there are many vibrational modes that are in the ultraviolet. There are not very many in the optical. So when you kind of divide these things up, this is sort of a standard thing that you'll see in the textbooks, which classify the how you can so delta J has to be plus or minus 1. So if you're, for instance, in the J equals 4 state, in the nu equals 0 state, you can only go to the J equals 3 state. That's it. And then that's also 3 can go to 2, or I'm sorry. Or if, on the other hand, you can compare these two things. It's possible to go from either J equals 4 to J equals 3, or J equals, well, they don't have an arrow there. Let's consider J equals 3. J equals 3 can go to J equals 2, or it can go to J equals 4. One is plus 1 quantum angular momentum, quantum one's minus. And so what molecular spectroscopists refer to these things as the P branch and the R branch, French for poor, French for rich. And then the one that consists of going from the 0 state to some other state, which is never allowed, it's called the Q branch, and that was just chosen because it's the letter between P and Q. But when you look at a sort of more realistic, this is again a toy model of what a real row vibrational spectrum would look like. It would look something like this, with the R and the Q. The lines are in this. It's a first order. When you're first thinking about it, these lines are all the same distance apart, and there's no Q band. That's not allowed. You never have one at delta J equals 0. Slightly more realistic, and this is still a schematic, row vibrational spectrum looks something like this. And so in the P branch, as you go to higher and higher transitions, they get spaced farther and farther apart, whereas in the R branch, they get spaced closer and closer together. And that's because as the energy increases, the R branch, the energy levels become more and more similar, but where at the P branch, the levels become less and less similar, I'm sorry. This has to do with two things. We say rotation vibrational coupling and also centrifugal distortion. So let me try and explain that. Sounds complicated. We assumed that the moment of inertia was constant. And this, let me go back a little bit. Let's go a little bit there. Oh, go back. No. I'm sorry. What? Thanks. Okay. Oh, what did I do? Where is that slide? Yeah, okay, here. In this equation, we assume this B, which has the moment of inertia hidden in it, is constant. But it turns out that when you think about when the amplitude of the vibrations get really large, that B is actually a B effective. It's a function of the vibration, which has some constant alpha effective frequency plus 1/2. So there is, as you start to, the vibrations get large, it starts to affect the moment of inertia. And then the centrifuge, that's the rotational vibrational coupling. So it's where the vibration is actually affecting the moment of inertia that affects the rotational levels. When the molecule spins very fast, it's pretty easy to understand that as it's spinning faster and faster and faster, it also stretches the spring a little bit. And as it stretches the spring and the atoms get farther and farther apart, the moment of inertia gets bigger. So then again, this B changes too. So that's what's going on here. Now, a real spectrum looks something like that, and there's some complicated things going on. There's some splitting, and I'll save that for another day. So, you know, the implications of molecules in the Earth's atmosphere is that, I mean, everything that's going on, this is the transmission spectrum of the Earth's atmosphere. So somewhere around, this is about 320 nanometers, the Earth starts to get opaque. That's due to oxygen 2 and diatomic oxygen, and to a large part the ozone. When people talk about the disappearing ozone layer, when the ozone layer goes away, then a whole bunch of ultraviolet light will get into the Earth's atmosphere, and we will start to get cancer. 5 minutes? Okay, good. We're almost there. And then there are these little notches. These are due to water, methane, ozone. Then it gets very opaque for a long time, and then you have this notch. This is why we can watch, listen to the. In the old days, we used to watch television, not streaming, and we used to listen to the radio instead of Pandora. But it was possible because there aren't many molecular transitions in this area. This is sort of a better picture of the near to far infrared, and you can see all this really, really beautiful, complicated structure with this is ozone, carbon dioxide, water. And then maybe I'll stop pretty soon because I do want to have a few seconds for questions. One thing to realize is when we talk about the greenhouse effect and global climatic change, is look over here, and this is the absorption percentage in the Earth's atmosphere. You know, these are wavelengths that heat the Earth. And if that radiation escapes, the Earth cools, and if it gets bounced back, it heats up more. And so the kind of interesting thing is that you see methane, for instance, nitrous oxide, carbon dioxide. You know, they all, they're all in this band that's very important to the thermal regulation of the Earth. And the thing is that if you look at the composition of the Earth's atmosphere really is nitrogen, oxygen, argon, and water. Water changes a lot, so I don't put it on this chart. But then when you get down to carbon dioxide, it's minuscule. And then these things like methane and nitrous oxide, you know, methane is tiny. It's like 1.8 parts per million. And yet, look what it does. I mean, look at it, for some wavelengths, it really, really absorbs a lot of light. It's a very, very potent absorber. If you look at nitrous oxide, it's 310 parts per billion. Carbon monoxide is 120. And yet, well, carbon monoxide is not such a big deal. But nitrous oxide, huge. And so when people say, oh, you know, no, I don't drive very much, I don't, you know, spew out too many pollutants, you know, it's very, very tiny, tiny amounts, changes in very, very tiny amounts of stuff that regulate how the atmosphere is. So the only thing I'll say is I had some other things that I put in, but I don't have much more time, so I would stop there. The only thing, my very last slide, is today turns out to be my mother's birthday, and she would be 95. She passed away. So I thought I'd dedicate this talk to her, and you can't see it up there, but it says happy birthday, Mother. So I'll stop there.
Thank you very much, Andrew. So we have about 15 minutes to some question. Okay, can you give me the thing? Jamila, thank you.
Thank you, Dr. Andrew, for this presentation. Well, you talked about the quantum mechanics, which is actually interesting and also complicated physics. One of the things that I want to ask about is that we know Xamon team use quantum chemistry or quantum physics to compute to work out what are the molecular spectra look like. So how they do this? How they calculate these line intensities?
Thank you, Jamila.
You know, there are several groups in the world that devote themselves to nothing but that. But for instance, I mean, it's very computationally intensive because usually it's sort of iterative perturbation theory, which is, you know, I showed you what it looks like if you take the Morse potential and expand it to third order. Well, you can go to higher order, but then that requires much more computation, okay? And you have to, and because it's purely numerical technique. I mean, you're not sitting down there, sitting with your, you know, your pencil and pad of paper and calculating an integral. You know, you have this supercomputer going chunk, 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 and then you compare it to the data, and they're, you know, sometimes I know they do this in atomic physics. You know, they'll decide that they've got the form right, but there's a little error in, for instance, the exact center of the wavelength. So they'll take the data to move the theory over. So the theory interacts with the data all the time. Oh, yes, absolutely. All the time. What? Yeah. Yeah, it's purely an interaction between the lab astrophysicists who measure something, but they're not perfect measurements, but then some aspects of that measurement is more trustworthy than the theory, but then there are parts of the theory that are more trustworthy than the experiments, and so it's a very complicated, as I say, my wife does this, so you know, it's a very complicated interplay where you try and make it better and better and better, because you know, when you take pretty good theory, and then you look at the experimental results, and you say, well, I should change some of the, and then I've got something better, and then that gives you a better experiment, and then, you know, so the theory and the experiment are always, so laboratory astrophysics is very, very, very important, especially for spectroscopy.
Can you introduce you, please?
Bonjour. Don't worry, I'm not going to ask the question in French. My name is Ammar Abdullah. I'm from the United Arab Emirates. Thank you so much, Dr. Andrew, for this beautiful presentation. What I wanted to ask is, imagine you have your telescope and you connected your spectrograph and you're pointing it towards, let's say, a variable star or binary star. You get the spectrum, you detect it using a CCD, for example. We get the telluric lines, which is fine. We can calibrate it and subtract the lines. But you touched on the interstellar medium, which is mostly made of hydrogen and helium, but also made of other complicated molecules. So how do we account for these, for example?
Thank you.
That's a good question. The molecules, well, it depends on if you're doing optical or infrared spectroscopy. Molecules are mostly infrared and then they're ultraviolet. So if you're doing sort of standard CCD optical astronomy, it's the interstellar medium. There is a skewness. There's some unexplained properties, but usually they don't matter very much. The thing is also the line structure from the line structure of the star, usually the first thing you do is you flatten it out, right? So, when the spectrum, if you had a spectrum over the whole visible wavelength, you'd have the spectral energy distribution would do something like that. So the first thing you do when you want to do radial velocity measurements is you fit, when I talked about continuum fitting, you fit the continuum and subtract the continuum. And so the trick is with stars that there's so many absorption features that you can't, was this the continuum or is this the continuum or is this, but so you flatten them out so that there's some chromatic there's a chromatic extinction, depending on how far something away. That's not really a big problem. The molecules, if you're in the optical, are not such a big problem. If you're doing a very, very precise measurement, which I'll talk about on Wednesday, what starts to matter is the molecular lines in the Earth's atmosphere. And so we call them they're called, well, of course they become macrotellurics. Water really turns on. We start to basically above 9,500 angstroms. There are people that go and work up there, but it's stupid because there's so much water absorption. It's essentially opaque. But even at shorter wavelengths, they're tiny things, but they change all the time. The water content is highly variable, and so when you're trying to get a really good radial velocity measurement, the fact that on Tuesday there was this much precipitable water vapor so there's an absorption feature this big, and then on the next Tuesday it's this big. If you're trying to do centimeter per second radial velocity measurements, it counts. And so the Earth's atmosphere is probably your biggest atmosphere. That's why people love the Webb telescope so much.
Sure. Thank you very much, Dr. Handy, for the nice presentation. Very important and rich in information. My question is, you speak about the way to measure hydrogen in the Milky Way. And what about for the molecules in the Milky Way?
Sure. I mean, there's a famous carbon monoxide map that, and it's distributed in a completely different way, but there's carbon monoxide. There's a continuum, spatial continuum of carbon monoxide. It was actually done from a telescope that was, New York and Boston are terrible. You can't have an observatory, but in CO you can. And so it's a little tiny telescope. It's sort of like this big around, and for a long time it was on top of the Columbia Physics Department, and then they moved it to my building, and they mapped the whole sky. Well, they had one in the south too, but it's a beautiful map. I could show it to you if you find it on the internet somewhere. There are lots of
Question for Moulin.
Yeah. Thank you, Andy, for your long, great talk, describing all about spectroscopy and how it started from the beginning. So I just have one question about the forbidden lines that we got from some like comets or nebulas that we got. So can you just talk a bit about what's different from this forbidden lines and normal lines, and what we can get from this forbidden lines? And because these forbidden lines, we don't get them in labs, so can we trust them and derive any physical quantity from these lines?
You know, forbidden lines are sort of, it's kind of an interesting thing because the first forbidden line that was discovered, you know, I have a little list of things that astronomers discovered before physicists did. Helium, dark matter, dark energy. And forbidden emission was one too. And in planetary nebulae, they saw this green light. And they called it nebulium because they couldn't make it in the lab. You know, because you actually, to do it in the lab, you know, you can't, I don't know, I don't do that stuff. But, you know, you need a very special set of conditions to get a bunch of atoms that are diffuse, and, you know, it's just, there's a lot of magic, and it was debated for years. But forbidden lines, you know, there are a lot of different aspects to it. For instance, it's how lasers work. Because what you do is when you pump a laser, you flash it with some really intense quantity of light, and then all of it, it's like a pachinko machine, and all the electrons go. But then a whole bunch of them end up in a forbidden state. And then if you have a way of stimulating it, if you get, it's like, have you ever seen anything about nuclear reactions where there are all the mousetraps and the ping pong balls, and somebody throws one ping pong ball and they go, pfft. Well, the thing is that once you get a whole bunch of gas, where a lot of the atoms are in forbidden transition states, it turns out that if you hit an atom with exactly the right wavelength for a forbidden transition, then it's allowed to transit. And so it's sort of, you imagine that one of the atoms goes through, if you have lots of atoms, one of them will emit a photon. And that photon goes and hits a couple of other atoms and makes more photons and hits more atoms, and so it sort of multiplies, and that's how a laser works. So it's pretty well understood. We use it all the time. I should know more, given what my wife does, I should know more about how, she doesn't work particularly on that. But I mean, the forbidden states are exploited all that helium. Well, that's actually a diode laser, but anything that has a gas is operating with forbidden. Does that sort of answer your question? Yeah.
I think the last question before lunch.
Thanks very much, and absolutely. Thank you very much for an incredible presentation. My name is Victor Kori, and I'm from Nigeria. I like the part where you said in the end we have to come back to the real world. And just for curiosity, is it possible that, take Mars for instance, our next door planet, had the whole atmosphere evaporated by the impact of spectroscopy and electromagnetic rays and all that, and then dried up all the water, and then it is what it. So is Earth facing the same danger today with what we've seen of the depletion of the ozone layer and all that? How much danger is this? Is it something close to what might have happened to Mars as a result of the impact of what we're studying today? Thank you very much.
Thank you.
So you're asking how dangerous greenhouse gases are? Yeah, we talk about the habitable zone. And so we say that in the old days, we said that there's a distance when you get too close to the sun, the equilibrium temperature of a planet will turn all the water to steam. And what turns into steam at the upper atmospheres, it will dissociate, and then the hydrogen and oxygen will go away. And then there's a distance where you're too far, and all the water will freeze. And so that's not a habitable planet either. And it was always said that, you know, Mars was outside the habitable zone and Venus was inside the habitable zone, and Earth was comfortably in the habitable zone. But in recent years, we've come to realize that technically speaking, the Earth is inside the habitable zone. There are people that argue, I'm not going to say it's 100% true, people that argue that the Earth is inside the habitable zone. It's only special circumstances of how the Earth's atmosphere evolved, how water was delivered to the Earth, that make it habitable. So it's not, you know, it's not just a simple, you know, in the early days people said, well, the sun has an equilibrium temperature, so 1 over r squared, that tells you how much radiation lands on the Earth, and then how much does the Earth radiate, sigma t to the 4th. When they're equal, that tells you everything. We now come to understand that a lot of different factors make the Earth work as a habitable planet. And so we don't understand very well, you know, the models are very, very complicated. Some of them are actually, the predictions are good, some of them are not so good. But it's obvious that the habitability of the Earth, given how close we are to either inside the habitable zone or very close to the edge, is very well tuned. And it probably does, the thing is, you know, when I talked about those gases, you know, 1 part, you know, 310 parts per billion, and it still matters. You know, it's a very fine-tuning process, and, you know, I hope people will be wise. They sometimes are.
Thank you. I think it was the last question before lunch. Is there any more question? So, thank you, Dr. Andy. Alors, en principe, donc, le déjeuner, il est à 1h30. Alors, ça ne sera pas ici, ça sera à la Cité d'Innovation, à 5 minutes de marche. Je pense qu'on a une visite de la Cité d'Innovation avant manger. Donc, on va y aller sur place, donc pour la visite. Et alors, je vous rappelle juste un petit peu le programme. Donc, 1h30. I will if you translate for anglophone student. Donc, 1h30 le déjeuner. Je pense que ça va durer à peu près 1 heure. 14h30, il y a le bus qui part pour l'UCA en principe direct. Donc, il y a la liste. Donc, merci de respecter la liste et le rendez-vous à 14h30. OK? Est-ce qu'il y a des questions? Oui, pardon. La Cité d'innovation, il y a le parking. Donc, c'est vraiment dans le campus, là. Oui, juste à côté. Donc, de toute façon, on va suivre le groupe. Ne vous inquiétez pas. Il y a le parking, c'est même pas... En façon, on voit le parking, donc il n'y a pas de... OK?
For our friends who speak English, so we will have our lunch just next to this university. It's just a city of innovation. After that, we will have the lunch at 1:30. Before having lunch, we will have a tour in the center. After that, we will meet in the parking to go to the UCAMOOC Observatory.